All right. Good evening, everyone. Welcome to week 9, the final session of our technician test prep course. I'm going to blow through. It's going to go pretty fast tonight. If you have to jump off, I totally understand. You just get the replay link and go to PrepperNet.com/tech and get your and be able to watch the replay from tonight. So how can everybody hear me? Is it everybody hear me? I'll give it a minute to get everybody in here. We're stacking up and we'll give it just a few minutes. All system to go here. All right. Loud and clear with Michelle. Okay. So I just wanted to give a heads up and let you guys know that on December 5th is going to be a Wednesday. In fact, next Wednesday, a week from today, December 5th, there is going to be a webinar, free webinar, live webinar with Forrest Garvin, the founder of PrepperNet. And I'm going to pop that link into the chat, and you can go. It's the link is a Facebook link, but you can go there and register. I put that in the chat, and the idea is so there's a documentary coming out on prepping, and it's called the Black Sky Event. The day the United States power grid goes down is more a possibility now than ever. And so a little bit of what he's going to be talking about is grid down, EMP, or sabotage to the electrical grid. And as we see the way that society is going, we're becoming so divisive that you can realistically see the stronghold of one ideology getting attacked by another ideology. And notice I didn't take sides there. It's a potential to happen. It can, we're getting more and more hostile with each other over our ideologies and finding less ground. So anyways, the power grid attacks, we're looking at CME, coronal mass ejection, EMP, electromagnetic pulse, could be cyber, cyber attack, or it could be cyber attack. A lot of, I'm out in the country and we even have a smart grid out here. Our meters are smart meters. They can read them at the office. So they don't have to no longer send meter maids out, stuff like that. So this course is going to be this webinar next Wednesday, December 5th, is going to be about a grid down situation, and it's helping promote this video project that is coming up called a Black Sky Event. When you go to the Facebook and register, it'll tell you all about it, give you a link to Black Sky Event. It's really cool. The people, the experts that they bring in on this are top-notch, professional, scientific grade experts. So check it out, put it in the grid. We'd like you to attend. I just want to remind you of that. PrepperNet is a sponsor of this class, so I kind of obligated to kind of promote that. So with that said, let's go ahead and jump in it. I'm going to finish up 8, and we're going to cover sub-element 9 and 10 tonight. So we should be able to blow right through it, okay? 10 is, I think 9 and 10 are the easiest out of all these. They really do. They really make just, a lot of them are just making sense kind of things. We deal with safety and antennas. So we left off last week with Delta 01 section of sub-element 8. And they're asking here, which of the following is a digital communications mode? And the fact is that all of these are digital communication modes. We talked about packet radio. 802.11 is, you may be familiar with it. It is the standardized protocol for Wi-Fi. So you have .11a, B, G, or N, and now we're up to AC. It has a lot to do with your wireless router in your house. But again, it's a mode to be used. And JT65 is a digital mode as well. So, and yeah, I've listed here a few methods, other methods that aren't mentioned, PSK31, MFSK, and giving you a little bit of an explanation on these. And remember, digital communications are simply just ones and zeros, off and on, true, false, right? Any one of those 3 scenarios is what digital communications are based on. So when you're watching your TV these days in digital, what is really happening is the signal is coming across as just ones and zeros. And that's why the signal is able to get out further, less bandwidth, and it's able to get out more clear and precise because it's just ones and zeros, and there's a computer board in your TV that is decoding that into a signal, to a picture. Okay? So, Jeff, Michelle will take care of you. I just wanted to recognize that I see you. So what does the term APRS mean? So really, APRS essentially is GPS positioning. Some of your top-end radios have APRS in them. There are some digital modes that we use in Amron. JS8 call is one of those that incorporates your position. You remember we were talking about last week the grid square, and I kind of showed you mine was EM98XX, and you could basically, if you could get a copy of the grid, you can narrow it down, and it's not hard to find which your grid square is where you're at, and that identifies you in a radio network digitally where you specifically are at. And then that allows Google has a site, an APRS reporting site. There's a couple out there. They're free, and you can go to them and type in a zip code or type in an address, and it will show you all of the radios in the area that have reported in to the APRS system and that have APRS capabilities. Okay, so again, it's just, and it uses packet radio. APRS is really important for packet radio because packet radio technology relies on APRS to position and judge where the next node, the next hop is. Remember I told you how at packet radio a message starts in Florida and it works through a series of hops, and it lands, and your message lands in nodes, and a node is just somebody's computer, and as soon as it enters, it leaves, and it goes on to the next node, and it passes on and passes on. And usually it gets passed through. There's electronic logs that create that data, that bullet that creates the data, the header, the thing that we talked about that contains. We talked all about that last week and the week before. But there's many things you can do with APRS. A lot of people use it on their bikes to track their progress. I don't know if you've ever seen. I've got a couple of friends that are um, uh, triathletes, and they are really big in CrossFit. And I don't know if you've ever seen it where I've seen it on Facebook where they'll tell you their whole route that they went for on bike that day, and it could be 20 miles, and you're thinking you rode your bike for 20 miles, and they'll show you the route that they used APRS to track that. APRS doesn't cost anything. It is built into the technology that you buy. So a Garmin watch, a Garmin GPS, as well as Fitbit, and there's just a bunch of them. All the ham radios companies, major manufacturers have a radio or more, one or more models that are APRS capable. So it doesn't cost anything. And even APRS has been used in, if you remember LoJack used technology that is not APRS, but the technology piggybacked off of what APRS had started. And if it wasn't for APRS, we probably wouldn't have had the LoJack system, to give you a little idea. So simply put, the APRS stations periodically send packets with information about the position of the sender and a bunch of other information. So I give you a little diagram of how it works up here at the top. Let me get my laser pointer. There we go. I give you how it looks, different setups. So Kenwood makes a handheld, and it has GPS, has APRS already built into it. But they make you seem like there's a separate module, like you hold the handheld in one hand and the GPS in another. They're really in the same radio. But APRS is very popular on 2 meter and 440 or 70 centimeter that we've talked about. 2 meter at VHF, it's very popular. And that one of the reasons why it's very popular is because VHF has very little, is susceptible to very little interference, not like HF. But it is used on HF as well, just not, VHF is the sweet spot where you can find it the most. Okay. So I give you a little idea here of how it all ties in. So the position is determined. It's converted to tones through a TNC box, a terminal node controller, and then it's transmitted out on radio through a digipeater. And a digipeater's job is, you will hear the term digipeater. Digipeater's main job is APRS positioning. They're all around you. They're not necessarily listed as repeaters that you can use because it's kind of an automatic system. It just works. Okay. And again, we go back to automatic packet reporting systems. So you're not doing anything to promote it. You don't have to put these digipeaters, program into your radio. The whole technology does all of that using satellites and built-in GPS to your unit and everything. So APRS proves especially useful. They use it a lot in search and rescue, so that your incident scene commanders can get a bird's eye view of where their assets are at, and if they get a report that a lost child or a lost hiker is in a particular location, they can look at what asset is closest to that and then get them on the radio and direct them. So, and we talked about packet radio. And you can use it to just kind of tell where I can go on, and I know my fellow operators in my area, and I can tell exactly where they're at. If they're in their car, I can tell they're going down the road. It reports like every 15 minutes, or I think it's about every 15 minutes. It's really in real time, but the websites that you get the information on, sometimes that's where the lag is. And it's usually only a few minutes behind. You got to imagine it's all the things it has to go through to appear on your internet browser. So, Race coordinators use it during races, like triathlons and bike races. They have what they call a rover. A rover is somebody that's in their car. Usually races will contact their local radio club, the local Aries chapter, because it's a free service. Aries loves nothing more at the opportunity to train, and these races are perfect. And they use APRS and their radios to be able to tell where the rover is at, where stations are at, and things like that. So shipping companies can use it also to tell you in real time where your package is. And you probably have somewhat used a little bit of it. Some carriers are a little bit more advanced than others. So next question, number 3. Which of the following devices is used to provide data to the transmitter when transmitting APRS from a mobile amateur radio? So when you think about positioning, out of all these choices here, there's really only one that really concentrates on, and it says it right in its name. You got position in the question and global positioning system, a la GPS, right? So we all use GPS to tell where we're located in relation to a satellite. Okay. So I gave you a little diagram here, and I gave you a little bit of an idea of what the bullet looks like. I call it a bullet, or the packet. What the packet looks like that's getting transmitted, and it tells the time, the latitude and longitude of where the sender is, where it needs, the altitude that you're at, and things like that. That's the kind of information that it transmits. Okay. And usually in your radio, in your car, again, and all that's one unit. You would not have a TNC mounted under your dash and the radio under your dash. Usually these radios have it all, in the GPS, it's all combined. Your car GPS won't have anything to do with APRS. It has its own, the radios that you would use, it's all self-contained, and it's ready to go. Okay. Oops. So you don't, if you get into this hobby and you have GPS, you have a car that doesn't have GPS, don't think that precludes you from having that capability. You just need to buy an APRS ready, capable radio. So what type of transmission is indicated by the term NTSE? So when you see NTSE, there's two technologies when it comes to radio. There's NTSC and there's PAL. Okay. And so when it refers to NTSC in terms of radio, they're talking about fast scan color TV. Okay. So if you ask a broadcast engineer what it stands for, he'll probably joke and say that it means never the same color, because his job is to keep all the cameras looking the same. And NTSC kind of messes with that a little bit. Now that we have the new standard of digital, where we don't have rabbit emitters anymore, or you're either using cable TV, satellite TV, or you're using a digital converter box. But NTSC is really more popular these days with amateur radio operators. And yes, you do have the privileges to be able to run your own little amateur TV station. You do. As long as you broadcast within the amateur bands that you have the privileges for, is perfectly fine. So NTSC stands for National Television Systems Committee, again, NTSC is not quite as popular anymore as it was in its heyday, but they pretty much were the governing body of television broadcasting standards. Okay. So I just give you a little picture here of what it looks like. You know, you got a camera and a mic. It goes into a transmitter, and that transmitter is hard set too. And you have a converter, a down converter box, and that's connected to an antenna. And that's how you broadcast out. So, and as you can see here, that, you know, this KB6, Kilo Bravo 6, Charlie Juliet Zulu is a call sign in California. It looks like he's just showing himself talking on his radio. Okay, and he's just broadcasting out his vocals over. And the reason why we use 440 the most is because there's more. You are allocated more bandwidth and much more of a range of frequencies to use on 440. Remember, on VHF on 2 meter, you're only allowed from 144 to 148, right? 4 megahertz is all you get. You know, anywhere in between there. But on UHF, I think we are privileged from 420 to 450. There's 30 megahertz. So I believe that's the range. So, and all you really need is, you just need a down converter box more than anything. There's a company, MFJ, that we call it Mighty Fine Junk, MFJ. They're not a bad company. We call it MFJ because sometimes you get a dud and sometimes you don't. Whereas if you buy a brand name like Kenwood, Yaesu, it's going to work. You're never. I've never heard of anybody getting a dead radio from on arrival from that was a Kenwood or a Yaesu or a ICOM, or, you know, it just doesn't happen. Their quality control is, and they test everything that comes out of their factory. MFJ, a lot of their stuff is made overseas. They get it and they trust that the factory is testing the stuff. So anyways, which of the following is an application of APRS? So what you can basically, you know, when you look at these other choices, you know, again, think of APRS like you know, if you know that GPS is combined with that, APRS encompasses GPS capability to kind of place you on a map. It's the only answer here that talks about a map and showing locations of stations. And when you read that answer, it really screaming GPS, right? So it's really the only answer that makes sense. So the reason why I've showed you so many slides of APRS is because it's really important for you to know what it does and what it is, because you're going to hear it. APRS is becoming more increasingly popular by the day. And the radios that support it are getting cheaper and cheaper and cheaper, where I would say in a handful of years, it's probably going to be standardized on most radios. And by the way, when you buy the radio, you can turn APRS off. It's not a you must use it. You can turn off the functionality within the radio if you're one of those that don't want to be tracked and be seen or whatever. So, and I'm basically telling you the components of APRS system are a GPS receiver, a ham radio transmitter, and a little bit of logic and hardware to connect the two inside the case of the radio. Okay. So when it's turned on, the transmitter is sending out packets that contain GPS coordinates, like I was telling you earlier. What does the abbreviation PSK mean? So PSK means phase shift keying. And this might be you might be easy to get this confused because we're talking so much about packet. But remember, on your test, you may only get one question that talks about packet. You may get 2 or 3. Don't let this confuse you, okay? PSK happens to be the most popular. PSK 31 is what it's called. It happens to be the most popular digital mode used. So I just give you a little bit of explanation of what phase shift keying is, and then explain phase a little bit. Phase is a kind of it's kind of a neat thing that how it happens. I have a headphone mic set that I use for HF when I'm training with Amaron, and I have a switch that I can change the phase. And when you're listening and I hit the switch, it sounds like the depth of the signal has changed. So when I have a lot of people piling up to check into a net I'm doing, I can flip that switch, and sometimes a station will stand out more, and I can slowly but surely pick them off and reduce the pile up, okay? Which of the following best describes DMR, digital mobile radio? So remember we were talking about the time multiplexing, how two signals can come into the same repeater, okay? So it's it's another one of the several digital modes that you have full capability for. DMR uses 440 megahertz or 145 megahertz range. When you buy the radio, it'll ask you, do you want the UHF or the VHF version? I will tell you to always get the UHF version, because there are far more, like we're talking a ratio of 10 to 1 UHF based DMR repeaters than there are VHF repeaters. And it goes back to that bandwidth, 4 megahertz versus 30 megahertz. So it's not a position tracking. It doesn't have that. And it's not a logging. It doesn't do log. Well, there is a website you can go to if you use DMR, and they have a section called Last Heard, and it keeps track of traffic that's passed through the network. And when you have a DMR radio, you have to request for an ID. It's free. But that ID gets put into your radio, and it becomes your address. Nobody else has that number. So when you key up to a DMR repeater, you're a number. You're not a call sign. It's like a street address for you that just always changes, because you can use DMR anywhere, okay? But this is what I was talking about with DMR. This is a normal repeater over here. Just one signal can come in, but DMR uses TDMA technology, which is time delay. I forgot what DMA stands for. But what happens is two people can talk simultaneously into the repeater, because it happens so fast that there's 2 time slots on a repeater. Okay, and these little packets here are their measurement is time. How much time is allocated to each time slot? So it goes time slot 1 2 1 2 1 2 1 2 1 2. And that's how I'm able to talk to my wife can be sitting next to me. She has a DMR radio. She can talk to somebody here locally to me while I'm on my radio talking into the same repeater to my dad, who's in another state. Okay. Which of the following may be included in packet transmissions? So the packet, remember we talked about this, the packet, it provides a checksum so that the full packet leaves the sender, it arrives intact to the recipient. So there's a checksum there that involves what size is the file. Okay, believe it or not, when you go to download things from the internet, there's a checksum to that as well. And one of the first data bit that hits your computer, it contains how big the file is for the download. And at the very end, it should have a tail that says end of packet, or end of download. and your computer, your operating system is already programmed, already has the algorithms in it to analyze how big is that file and does it match what the header said. Okay, so, and if it doesn't match, it automatically requests a repeat. And in ham radio, that packet it contains the call sign of the transmitter as well as the call sign of the intended recipient. So I've kind of put this here to you to give you a little bit of an explanation. And this is how it kind of looks. The first recipient is the header. And then the payload contains all the actual message itself. And then on the end, how big the file was. How big was the packet that was sent. And the recipient has the same technology. It then goes and checks the checksum and sees if it agrees with the checksum of what it's received based on what the header said. Thank you, Beth. That was it. Thank you so much. TDMA, time division multiple access. I forgot what I thought it was. Time delay, time division. I know what it is. I know, but it's not something that's on the top of my mind every day, but you get the idea. There's a division of time between two slots. What code is used when sending CW in amateur bands? Well, by now, because of all the other sections that you will hopefully have studied, you know that CW means continuous wave. All CW is the carrier tone. You remember I showed you the carrier and the two sidebands? Take out the sidebands, and all you have is the carrier tone. And CW just opens the circuit, creates the tone, and closes it. And it opens it up for a period of time before it closes it. And other times it's open, close. And that's how you get the dit, da, dit, da. Okay. So I give you a little bit of an explanation here for sake of time and what we have to go through. I've given you enough here that you can go back on review. Okay. So whether or not you remember what it stands for or not, every amateur radio operator should know that CW means simply Morse code. And this, you're familiar with this. And all that is the carrier tone. The carrier is, circuit is opened for a period of time, and then it's closed, and that's the gap. And then it's open for a period of time, and then it's closed. These other ones, these dots like the number 5 here, it's open, close, open, close, open, close, open, close, open, close. Number 6 is open, close, open, close, open, close, open, close, open, close. Get it? So which of the following operating activities is supported by digital mode software in the WSJT suite? So the reason why you're being asked this, and I can't tell you if it's going to be on the test or not, but because as a technician, there's enough things that are kind of unique to VHF and UHF that if you care to experiment and explore, there is, there's a host of things out there you can do. You can send a signal with a directional antenna pointed at the moon, and you can bounce your signal off of the moon and get it halfway around the world. Okay. And you might send a signal that says, I'm in North Carolina, the blah, 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 KM4ABC. I'm in North Carolina. My email address is, hamtech class or mercury01 at preppernet.com. And they hear it on that other end. They can email you and say, I received your signal in Spain. It's really cool. I don't do it. And that's why I told you, I'm an extra, the top end. But it doesn't mean I'm smarter than guys. It just means more privileges. And I say that because I've seen some technicians that do stuff with moon bounce or earth, moon, earth, bouncing signals off a meteor scouter. I mean, it's just amazing stuff that I never do. So if it interests you, it's there for you to be able to do. And WSJT is just simply, it's a software that kind of encompasses a lot of things. There's a lot of things that happen in this software. It's free. You don't pay anything for it. Free download. And WSJT, JT65 is a digital mode that uses this software, and JT65 specializes in very weak signals. You can pass digital messages on very weak signals using JT65, and you would use this software for that mode. Okay. And I'm just giving you a picture here of what it looks like. And it's not hard to really figure out. I used different software for different things, and you figure them out. You eventually, when you look around in it, and in real time, you see this stuff moving in real time. So, and it gives you some Doppler. Remember we talked about Doppler shift, and where the moon is in relation to you, based off of your grid square and the sun and stuff like that. So, give you an idea. And here you see they're passing a message to Sierra Mike 7, Bravo Alpha Echo. And this is the message that they're saying, and he's sending you. You can have a couple of canned messages that are pre-formatted, and you just pick which one and then transmit it. Pretty cool stuff, and you have access to that. So don't think that you getting your technician isolates you just to a Baofeng. No, 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 no. So what is a RQ transmission system? It stands for automatic repeat request. And so when a receiving station detects an error, it simply just asks for a repeat and asks for a resend. That's really all. So it doesn't have anything to do with encryption, because anybody can pick up the signal. And it does, when packet radio, it can take a little bit to get the message, to receive the message. And if it doesn't go right, you have to turn around and ask for a request and then get that message again. That process can take a little bit. We're talking several minutes. A packet radio, a message could take a couple minutes to send. It's not completely unreasonable. A lot of times it's short, but it can have a tendency to go long. Which of the following best describes broadband hamnet, which is a trademark technology, also referred to as high-speed multimedia network? So this is another thing, again, that goes back to technicians. With VHF being repeater-based, technicians have found a way to use a very specific router. They're very common. When I show you the picture, you most definitely have seen this kind of router before. But it was one time, it was basically a mesh network. Okay? And basically, it's kind of a Wi-Fi network, but it's not based on internet. It's using radio signals as the Wi-Fi. So it's using the antennas and the receive and transmit capabilities of the router combined with the radio to send signals to nearby. So if you have a community, if you have a mutual assistance group that's spread out, over 10, 15 miles, a mesh network is really good. You can use that to be able to communicate with each other. And think about how few people are facilitating this. And you just have to read and learn. Again, with ham radio it's a geek hobby. And the reason why it's a geek hobby is because there's so much to learn, and anything you want to do to your heart's desire. I think I've probably in this class have mentioned some things that probably have blown you away, and you're like, wow, you can do that with radio? Because your probably impression, like mine was getting into it, was it's just voice. You give the call sign who you're calling to, you give yours, and then you talk. But there's so much more to the hobby, and if it can be done, a ham radio operator will find a way. Okay, so this is it's a Linksys router, a very specific router. It's like a W54G or something like that, but it's very specific. And if you go out on Amazon you will find these routers being sold for, hell, you can buy one for 20 bucks now, 25 bucks used. They don't make them like this anymore. The ones that they make now, you know, are AC speed, and they have other technologies in them that have kind of lost this ability. So you can find these out there. They're everywhere. Okay, real cheap too. And I wanted to give you an idea of how it looks. I hope that pictures. Hey, Richard, good to see you, man. I hope these pictures help solidify an image and give you substance to concepts that you've never heard before. So I hope the picture, like, I'm a picture person. If I don't understand it, show me a picture. You know, I'm a sophisticated gorilla. That's all I am. My wife would agree. So, you know, this is pictures help me cement an image of what is being asked. Okay. And this is what it looks like. Really, it's simple. It's really simple as this. Really. And you got a webcam. It's plugged into the router. This one's probably connected to the internet. It looks like it. No, it's got the antennas, and the radio is probably inside this box. You know, a lot of comms centric preppers love using ammo cans and ammo boxes as a go box. We call them go boxes. All my radios are in cases, road cases. So all I have to do is unscrew, pick up the whole case, and I can take all my radios in one trip, put it in the back of the truck, and I'm down the road. And this is the same concept. This probably goes inside here. There's probably a power supply, a lot of stuff. So all this guy has to do is grab the box and a laptop. And that looks like a Toshiba Tecra old school laptop. I've had one of those. It looks exactly like that. So I'm sorry, I'm under pressure. I'm under time to try to get this done tonight. We still have two more sub-elements to do. They're rather short, so I can't really go back. You'll have to go out to preppernet.com/tech and get the replays in another day or so. Right now, it is completely updated up to last week's. You should see 1 through 8 out there. I checked it and it's out there. I just have to load 9 and 10 that we're about to go into next. So what is FT8? You know, a lot of the things that we've covered in this class really are truly HF radio. You know, worldwide radio, we like to call it. High frequency radio. The reason why you're being asked these questions is because you remember I told you that you can fully anticipate that the FCC is going to start opening up a sliver like they do on 10 meter for technician. They're going to open up a sliver on 20 meter, 40 meter, 15 meter, 80 meter. You know, they're going to go all over. In every band, you're going to be able to have a little sliver for. So and this is a cue to tell you that it's true. ARL has been talking about it for a while. This is proof in the pudding that it's going to happen. So it's very promising for you to come in as a technician because you have that you're going to get those privileges. So they want you to know just a few things about HF. That's why you're seeing questions regarding what deems for you right now to kind of be out of. But you know what? You have 10 meter and you can do FT8 on that little sliver of 10 meter that you get. So it's just a digital mode. It's capable of operating in very low signal to noise, weak signal we call it, conditions. And it transmits on 15-second increments. So with FT8, it's kind of a beacon. And if you want to hear what local stations are near you, you know, I can bring up my laptop, turn on my radio to a certain frequency, And with Amron, we use a frequency on 40 meter a lot. And at any given time of the day, I can let that run, and I don't have to be in front of it. And it will go throughout the day, and it will beacon out my signal, and it will listen for other Amron operator signals, and I can see how strong they are. And if I know who they are, a lot of times I know where they're located, and I can tell that I'm getting a good signal from Missouri or a really great signal from Idaho. So again, FTA, it's new. It's relatively new. It's just really come on the market. I think in 2017 is really when it became we got standardized. So I was really surprised to see it, something so recently developed, hit the test. But FT8 took ham radio by storm. And again, it's because it's so exceptional with weak signal. And right now we are at the bottom of our moon phase, our solar phase. And we've had, for the past couple of years, the bands have been really challenging for Amron. So it appears that we're coming out of that. So this FT8 weak signal mode came to fruition based on such difficult conditions, atmospheric conditions that we've been facing for the past few years. I've had nights where the conditions were so bad with solar flares that digital wasn't even working. And that also poses a challenge too for ham radio. That's part of the challenge. And this is what FT8 looks like. You remember the waterfall I showed you? You're going to find the waterfall to be a mainstay in digital modes, because what it does is when you get good at it, you can just look at the signal and tell what kind of mode it is. Okay, this particular software really only looks at FT8, but it also will show other modes in here. But it's only going to be able to detect and decode. I'm sorry, it will detect all different modes, but it's only going to decode FT8 signal into text. And you're seeing some of that happen right here. Okay, it's being transmitted, and you've got some pre-canned, what we call macros. You just hit this one button and it automatically transmits out CQ, 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 and your call sign. You just have to hit one button. And that's the great thing about digital radio that I love so much is that, you know, with Amron, we use the KISS method. Keep it simple and stupid. And so a lot of our traffic is almost predictable. So we just set macros, and all we'd have to do is just hit one button, and it goes in the back end settings and pulls my call sign, and then whatever I've set that macro to say and transmit. Sometimes it may be hello, you're a jerk. Anything I want, I can set a macro to it. Okay. So what is an electronic keyer? Really, it's just a way to facilitate and to use Morse code. And you've seen one. They're old school. They've been around for a little bit. I say they're old school. Electronic keyers have been around for a good 25, 30 years. But what they were really key to do was to replace the telegraph paddles, the old school paddles that they would use, because it would hurt people's wrists after a while. The electronic keyers, the way that they're set up is you just set your hand on the desk on the side of your palm, put a finger on each one of these paddles here, and one does the dots, the dits, and the other one does the das. And when you get good at ham radio, you just sit there and move your wrist back and forth, and it's just a much more comfortable feel to it. And this is an electronic keyer here. I put a screenshot of FL Digi on here because, again, it goes back. You see these very narrow signals. You remember I told you that was a telltale sign of being Morse code. Well, you can, if you don't understand Morse code, it's okay. there's some purists out there that'll probably want my head on a platter for saying that, but it's okay because we have software that when I type the message down here in the blue and I have CW selected, it'll automatically transmit it in dits and das, whatever I've typed in this little window here. And, and these are other signals here. Okay. So you got three incoming signals, and I'm willing to bet it was this one here and these two right here. So I just want to give you, and this again, FL Digi is free. Don't pay anything for it. It's the most common digital software that we use in Amron. It's standard for us because it's freeware and it's easy for us to help each other when we lose a configuration or something gets corrupted. Okay, that's the end of section 8. I'm going to bring up section 9. And let's get started on section 9. Okay, here we go. Section 9. I've got to sign off now. Class has been terrific. We'll catch the rest of the replay. All right, Beth, great attitude. If you guys take the test and you pass it, send me a message on Facebook or in the PrepperNet Facebook page or DD12 Facebook page or the 3%ers Facebook page, because I see those and it just lets me know. It kind of helps me gauge my success rate. It helps me improve myself. Okay. So if you do take the test and when you do pass it, email me or put it on the Facebook page and I'll see it. And of course, if you have any questions, email me those too. So let's jump into it. Sub-element 9, antennas and feed lines. Okay, I tell you what. How about we stop for a couple minutes and go take a wee break and say 4 minutes, 3 minutes. We'll come back at 8:55 and we'll jump on section 9. Meanwhile, I'm here. I'm not going anywhere. My bladder's fine. So if you've got questions, an opportunity, I'll certainly answer them for you. Any questions? 2 more minutes and we'll jump right back in. And I may run late tonight. I mean, I'm really trying. I want to get through this before I got an hour. I may very well go to 11. And if I don't have an audience, that's fine. My purpose is to get this recorded and for replay so it's out there. I can't put something on the PrepperNet site that's incomplete and just say, oh, well, we only got done with section 9. Sorry, I couldn't do 10. That doesn't make for a complete course. So if you got to leave at whatever time, I totally understand. Let us know you're signing off and just let your computer keep going, or you can go to the replay and you'll see everything. Because this is our last night, I really don't want to have another class. There's no reason to. As of tonight, you will have all the tools you need to study. So one of the things I want to say is I've had comments that folks have said, well, you could teach a shorter class with just the answers, and I probably could. But in a case where you're taking a test, a lot of times it's better to have too much information because all of us digest it differently. It's better to have more information than you actually need, so that hopefully my hope is that you will find something in there that you can extrapolate, you can pull out of, and help memorize the answer. Okay, so my critics can go pound sand, I guess, in a nice way. Much love to you, but I teach it a little bit long method like this, so that you have a little bit more than you need. I've had folks that told me, I've waited years for this. Well, really, years? It's kind of a simple test. And when I hear that, that tells me that I need to really, I have to give a lot of information and give substance to the class, a lot of substance. So that's why it might seem long-winded to some. Will I be teaching a general class? I'm not sure yet. I'm really not sure yet. These are really take a lot of it. They really do. I've enjoyed it with you guys. I really have. And for that reason, I usually teach the tech class. I think I've only taught one general class, one, maybe. So general gets complete, it leaves VHF and UHF and it totally gets into HF. General covers a lot of antennas and a lot of antenna logic, because that's the class that you're using for HF operations. And general class doesn't really talk a lot about the rules and things like that. So to answer your question, I'm just not sure. Well, I'll take it under advisement, and see if I have the time. If I'm able to do it, I've told some people that I'm going to try, but I haven't committed to it. I'm going to try to do one in January or possibly February. I just don't know yet. So my work is piling up at work. I'm in information technology. I'm a computer programmer, so that's really piling up. We've got a lot of people that are retiring and stuff. So, and family demands and stuff like that. So, yeah, sorry, I just wanted to give you a full qualified answer and give you some respect to what you're asking. But I'll go the same method. When and if I do, I'll broadcast it the same way I did this class using the same method, and you should be quite comfortable with it. It'll be delivered the same way. So, sub-element 9, antennas and feed lines. You can expect 2 questions from this pool. There's only about, in this question pool, there's approximately 30, 35 questions in this particular sub-element. And out of those, 2 will be pulled. So let's jump right into it, okay? What is a beam antenna? Well, you got some answers here. And we don't really concentrate on, we don't really care. How does it help you to know who invented it? What substance does that have to you being a ham radio operator? I would just say. So that answer just isn't meaningful. They're asking you what is a beam antenna, not who created it. And I don't even know if Clarence Beam is the guy that, beam antennas really are just directional antennas. Okay, that's all they are. We call them directionals. You probably heard the term Yagi. It looks a lot like the old school TV antennas, right? Well, it is. That's exactly what an old school antenna what used to be. TV was a Yagi antenna. Okay, and you can really draw a similarity to this, because the idea with a beam antenna is that you want to beam your signal in a very specific direction into a very specific recipient. And that's why your TV antenna, it always mattered. You always pointed in the direction of the most the most TV towers. And if you probably remember, Grandpa probably had it on a rotator, and he pushed a button or on his rabbit ears, and it would actually turn that Yagi around. And he might have tape or a marker marking where the different stations were on that little dial. So that's all it is. Which of the following describes a type of antenna loading? So what they mean here is inductors are used. You remember, inductors are just coiled wire, right? And all an inductor does for an antenna is it helps, it makes the antenna believe that it's longer than it is. So when this wrapped around this PFC, PFC, not in the Army, PVC pipe, if you stretch this out straight, you may have 15 feet of wire. And if you connect your antenna on one end of that wire, as you can see right here, and you connect it on the other end, the antenna now thinks it's 15 feet longer than it physically is. Okay? And what that enables you to do is be able to put up, a dipole. Remember we talked about a dipole, which is just a horizontal wire with a center conductor that has wire feed line coming down the middle. Whatever frequency, the thing about dipole antennas, they're compromised antennas, meaning they're kind of meant to be multi-purpose. Some people have dipole antennas cut specifically to 10 meter or 20 meter or 40 meter. Okay. I have an antenna that has two of these coils on each leg. So on my antenna outside, I've got 4 of these all together. My antenna is only about 50 feet long, but because of these coils, I'm able to get up on 160 meters, which normally would require an antenna that's over almost 300 feet long. Almost 300 feet long, but by putting these coils here, I'm able to reduce it down to 50, to a little bit more than 50 feet, okay? Which of the following describes a simple dipole oriented parallel to the Earth's surface? So if it's parallel, think of Earth. When you think of the Earth, you think of the horizon, right? When you look off at a distance, the edge of the Earth is the horizon. They typically say approximately 6 miles from where you're standing is where the horizon is. Approximately for you, with the curvature of the Earth, you're only really seeing about 6 feet out before you lose perspective. So knowing that, when you think of parallel to the Earth's surface, well, that's a horizon. Well, there's only one answer here that's horizontally, horizon polarized antenna. So if that helps you there. So the orientation of the conductor of the antenna relative to the surface, Earth's surface, determines its polarization. So if the antenna is vertical, as most antennas are, it's thought to be vertically polarized. If the antenna is horizontal, parallel to the Earth, so your baofeng, when you hold it up to your mouth, your antenna is vertical. Okay? It's vertically polarized. So if the polarization of the sending station's antenna does not match the polarization of the receiving station, you can kind of anticipate a little bit of loss in signal. You'll still hear the signal, but you won't hear it as far away before it becomes unintelligible. So I give you a little picture here of the difference between, and when they're talking about, you remember when we talked about an antenna, the signal, it has a magnetic field, and then perpendicular to that you have the electric field, because what is a radio signal? It's an electromagnetic signal, right? Well, when we talk about polarization, we're talking about the electric field. And if you know anything about electrical in your house and things like that, polarization is important. it plays an important part of it, and you'd be very familiar with polarization when we're dealing with electrical. So that's the way you can remember. We're talking about the electrical field of the signal, not the magnetic field. What is the disadvantage of a rubber duck antenna supplied with most handheld radios when compared to a full-size quarter wave antenna? So what they're talking about is, smaller antennas use electrical components, not the antenna itself, to maintain the resonance of the targeted frequency. It uses electrical components because the antenna is way too short. A rubber duck antenna is to have any resonant quality on 2 meter. 2 meter, typically there's a formula to it, and I just don't want to confuse you with it right now, but it's real easy to tell how long a 2 meter antenna should be, and I think around a yardstick, about the length of a yardstick. But having less surface area on those rubber ducks, they aren't able to absorb or emit as much power as the larger antennas do. So they don't transmit or receive as effectively. So the general rule of thumb is the shorter the antenna, the worse the performance. Of course, there's other factors that go into. There's a lot of factors that go into your antenna. Everything affects everything. It's just like a car, right? The transmission affects the speed. Your tires affect your speed. The octane of your gas. It's like everything plays a little part into the big picture. And what I did here was I just tore open the antenna to show you what it looks like. Now, if you were to take this and you were to stretch this out, do you notice how the winding is a little bit tighter down at the bottom than it is at the top? If you were to pull this wire out to a straight line, you probably could get a couple of feet out of it easily, right? The problem with these rubber duck antennas is that typically the ones that come with your radio are POSs, all right, certifiably POS. I always recommend when you buy a Baofeng to go out and buy either it's called a Nagoya 701 or a Nagoya 771. And the only difference between those is the 701 is about 7 inches long and the 771 is about 14 inches long. Okay. They both will work on 2 meter and 440 or 70 centimeter. But the longer one works a little bit better on 440, meaning on 2 meter, and the shorter one works a little bit better on 70 centimeter. But they both will work. So just want to tear it open for you. So there's kind of trade-offs, to using a rubber ducky. If you're a security guard or you're using, you're like doing comms for a race or a ham fest or a gun show, or you're all in the same building. Rubber ducky doesn't matter. It's going to get out a couple football field lengths, right? We're talking the difference between a couple football field lengths and a couple of miles. Your antenna plays into that. But typically most of these rubber duckies go on a handheld. It's only 5 watts to begin with. You're not having a lot of power driven behind it either. So how would you change a dipole antenna to make it resonant on a higher frequency? So if you remember in previous sessions, we talked about higher frequencies have a shorter antenna. Lower frequencies have a longer antenna. Okay. So a dipole antenna for a higher frequency, say 440, is or 70 centimeters is very short. Well, you typically wouldn't, because 440 and 2-meter or ground wave. You remember, typically the antenna really needs to be vertically polarized. So it needs to be like a whip antenna, like on your car. Okay. But for HF frequencies, you would typically shorten it to make it resonate up on a higher frequency. So it's inversely related to the frequency. The higher the frequency, the shorter the wavelength. Okay. It's just the way it goes. It's always been that way. The lower the frequency, the longer the wavelength. What type of antennas are quad, Yagi, and dish? Remember when I told you when you take this test, sometimes if you get hung up, keep going. Don't stop, because sometimes you may run into a question that helps you answer another one. Okay, so this refers back to the beam antenna, you remember? The directional antenna, and those are quads, Yagis, or dish, you know. So a dish, you know, if you've ever seen a guy come out and put a dish up, you know, he's pointing it to the satellites, and he's usually got he's got a handful of satellites that he can position, that he gets a choice of. So when he comes in and he plots out your, you know, a layout for you to get dish, he kind of thinks, okay, these trees are in the way, this building's in the way. What he takes all these things in consideration, and what he has a program on his cell phone that he can hold up in the sky, and it transposes artificially where the satellites are at. So he turns on his this program. It uses his camera, and he just looks at this up at the sky, and he just turns around in circles, and a dot will appear where that satellite is. And by doing that, he can sit here and he can look, oh, look behind my phone, there's trees. That's not going to work. And he'll keep turning and turning and finding another dot, and then he'll say, oh, that one's wide open. That's where I'll point the dish. So these are all examples of beam antennas, which are just directional antennas, right? A beam antenna, you want to beam your signal in a very particular direction. Yagis are the most common. You see them all over the place. So what I've done here is I've given you each type. A satellite's pretty easy. A Yagi's pretty, you know, we've already discussed it. It's like old school antenna. But what you haven't seen is a quad antenna. And we haven't talked a whole lot about quad antennas. So I wanted to give you a picture of what one looks like. And typically it's 4 arrays, loops, that are situated along a horizontal plane. Again, hope pictures give you substance of what the heck we're talking about. What is a disadvantage of using a handheld VHF transceiver with its integral antenna inside of a car? Well, there's a couple things. First of all, the metal in your car will block your signal. But here's another thing a lot of people don't think of. As of late, you know, new car manufacturers, it's all about gas mileage, right? EPA says your car has to meet a certain gas mileage. And the way that they've accomplished that is it's a little bit harder to buy an 8-cylinder car anymore, if you've noticed. Even what used to be a 6-cylinder is now a 4-cylinder with a turbo charger on it. So they fool you in thinking you're getting that V6 response, but you're only pumping 4 cylinders in your motor. The reason why I say that is because they try everything. I bought a new car a couple of years ago, and it didn't have a spare tire. It had a pump and a bottle of slime, the green run flat slime. That was my spare. If you wanted a spare, you had to pay $100 for a small little donut extra, because of weight. They look at the stock, you know, the specifications say, you know, EPA says it must get this amount of mileage going at this speed with this carrying this much weight. So they nix the spare tire. Well, one of the things that they do is, and I get to my point, is they have cavitated glass. Your windows in your car have always been tempered. Well, they have been for many, 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 many years. And that just means they're laminated with an acrylic plastic on each side of the window, so that when it busts, it spider webs and doesn't shatter and fly as much without the tempered in it. Well, what they've done now is you don't even really see it, but there are really small metal flakes that are baked into the glass when they press the glass, and so you don't really see those metallic flakes. But what that does is it also contributes to hindering a radio signal that's inside the car from getting out. And so rubber antennas they're really subperforming antennas. They really don't perform that well altogether. But it's the trade-off that you take to be able to be mobile, right? And when you're in your car, the doors, the roof, all that metal is hindering that. The engine block, if you're unfortunate to have a car that has plastic panels, then it's not as much of an issue for you. But, typically most of the time, your quarter panels are going to be plastic, but your A-pillars, the actual roof of the car, the supports there are going to be metal, because the National Transportation Safety Board has kind of dictated that it needs to be able to survive a rollover and not crush you. My point is that all these things, and then you take in consideration these newer glass, solar glass. Now, the reason, and they call it solar glass, the reason why you have solar glass is to help transfer heat away from the car. That way your AC unit is not working as hard, bringing down your mileage. That's why it plays into it. It keeps your cool cooler, and also it adds to the sale appeal. When people say, hey, my car is, my wife drives a 2018 Toyota Tundra and I drive a 96 Cherokee. We park them in the same driveway side by side, and her car doesn't get nearly as hot as mine. That's why. Okay. Also, rubber duck antennas can tend to be long. If you have that 14-inch antenna and you're in your car talking, that antenna is rubbing against the headliner. It's bending because you can't get it in a straight line. Typically, your mouth is closer than 14 inches to the roof of your car. If you get in your car and you look up ahead, you really most of the time only have an inch or two between you and the roof. Not unless you have a vertically challenged spouse. That the distance may be greater. But the point is, you go to bring a bow thing up to your mouth. Now that antenna's got to bend when it hits the roof inside. And now that it's hitting the roof, it's coming a lot more in contact with the roof of the car. It's much closer to a metal object. Okay. What is approximate length in inches for a quarter wave vertical antenna at 146? I know your mind is probably blown right now when you see questions like this. What I hope to do is kind of give you an easier way to make sense of it. So 146 is in the 2-meter band, right? You remember we divide 300 by 146 and we come out to 2.05. So we're close enough to be in the 2-meter band. 2 meters, which is about 60 feet. I'm sorry, is about 6 feet. 2 meters is close to 6 feet. Is 80 inches. Is almost 80 inches. What is 1/4 of 80 inches? 20 inches. Well, the only answer they provide you that's as close to that as possible is 19. Okay, so that's how we come up with that number. Yeah, or a moonroof. I had a car that had an all-glass roof. It had what do they call that? A panoramic sunroof from front to back, and it was solar glass, and it didn't do me any good. And so what you were talking about, I had to open my sunroof and let my antenna stick up above, and literally that's how I was able to get around that. But as you know, a lot of people, sunroofs are an option. Not everybody has one. So if you have one, great. But you're exactly right, Richard. That's what I had to use to get around that. So this is this is how we come up with that 19 inches. Okay. What is the approximate length in inches of a half wavelength 6-meter dipole? So again, one way that you can do that is in ham radio, there's two numbers. There's two numbers that you need, that you can, really three: 300, which you've been aware of, 468, and 234. And the reason why, if you want to get a half wavelength, you divide your frequency by 468. If you want a quarter wavelength, you divide it by 234. So what I've done here is, you remember 300, we've got the bands, 6-meter bands. Divide 300 by 6, you get 50. Divide 468, which is a half wavelength, by 50, you get 9.36 feet. So when you've got 12 inches in a foot, multiply 12 by 9.36, and that's how we come up with the 112.32. This may for you be a question where you just have to memorize it. You just have to commit to it. Okay? But if I give you the math a little bit, you can if you really think about it and stop, don't rush. These tests are not timed. Take your time. They're not going to sit there all night for 4 hours for you to answer 35 questions. Who would? But they're not going to rush you if you take an hour to answer 35 questions. Okay, that's almost 2 minutes. Even if you take an hour and a half, 2 or 3 minutes per question. They understand they're not rushing you. There are many factors that will affect the amount of length needed for a half wave. Okay, so what kind of material is it made out of? Is the antenna made out of? The wire that's being used. You can use aluminum stranded wire, you can use copper core wire, or you can use copper clad wire that is a tin or aluminum coated with copper. All those have their unique characteristics. So again, another way that you can solve this problem is to remember that a meter is a little longer than a yard. So it's approximately 39 inches. To calculate this, half of the 6-meter wavelength would be 3 meters. To convert that to inches, you just multiply 39 inches per meter. And it comes out to 117, which comes as close as you can to the answer. There's no other answer that comes close to 117. In what direction does a half-wave dipole antenna radiate the strongest signal? So all antennas are going to, not all antennas, but most antennas radiate a signal broadside to the antenna. Usually somewhere in the middle of the antenna. So your baofeng, when you pull it up to your mouth to talk, the antenna, if it's 7 inches, it's ground wave, you remember? That signal is radiating parallel to the ground because the antenna is vertical, so the polarization is vertical. So the radio waves emit out along the length of the dipole outward, and the strongest is at the middle. Okay? So if you have an antenna that is cut to 80 meter, because 80-meter antenna is longer than one that you need for 40 and 20, you can realistically broadcast and transmit and receive signals on 20-meter, 40-meter, and 80-meter. However, you've cut it to be resonant on 80-meter, meaning you don't need an antenna. The SWRs are going to be really low on 80-meter. If you want to use it on 40 or 20, you're going to have to use your antenna tuner to fake the circuit. So, again, I told you it radiates broadside. There are some antennas that radiate that equally on all sides. The feed line has no effect on the emission of an antenna. A feed line does not. It emits your signal, but it's very little. If I had feed line going up to my antenna in my front yard, once I get past my neighbor's yard, that's probably, if I didn't have an antenna hooked to my coax and all I had was a coax up in the air, the signal is going out the end of the coax and out of that fitting that would normally be screwed into an antenna. My neighbor, once I get past my neighbor's house, I'm probably not going to hear the signal much. It's not going to, or once I get outside of my neighborhood, it probably is not going to be heard. Okay. So one of the things that we use a lot of times to kill that, just that little bit of signal, because if a signal can radiate, it means it can receive as well. So if your feed line is radiating a little bit of a signal, it means that it's also susceptible to receive some signal. And the way that we get rid of that is with a balun, B-A-L-U-N. Okay. And what I've done here is I've taken the picture inside of what a balun is. There's two types of baluns, just for your information. It's not on the test, but there's voltage baluns and there's current baluns. And they can be 1 to 9, 1 to 2, 1 to 4, 1 to 1. And really what sets that is how many windings around an iron toroid that we use. And each leg of this, we would have a loop connector, and we would screw it down to each end of these and then run the wires out either side. Okay. And then you can see where the jack where you would screw in your antenna. Which is the gain? What is the gain of an antenna? So gain is simply an increase in the signal strength in a targeted direction. If an antenna is a beam antenna or a directional antenna, you can expect to have much better performance because all of your power is being directed in that one direction. The entire signal is being directed in that one direction. So all the power and effort of that signal is going in that one direction. Whereas like your antenna on your Baofeng or a dipole antenna, like a horizontal wire antenna, it is transmitting all around 360 degrees. Okay, the signal's going up, it's bouncing off the ground, it's bouncing off the buildings. So think of gain as a quality of an antenna. Think of it kind of like the reflector on a flashlight. If you have a grainy mirror behind it, yeah, it's going to flash the signal out. It's going to broadcast that light out, but not as much if that reflector behind it is highly polished. Okay, so by the geometry of an antenna, we can change how the antenna emits radio waves. So, like we can focus a spotlight by using, we can focus it like a spotlight, by using a Yagi antenna or a quad or a dish, or we can let it flood out more evenly like a room shop light. So in other words, if you have a spotlight, you're specifically directing that light in a very intended direction, like a beam antenna, or like the light bulb in your ceiling or in your kitchen. It's radiating everywhere. It's illuminating the whole room. If you ever seen somebody use a spotlight, especially like on a car, the only place that it's lit up is where the beam of light is. You go to the back of the car and it can still be pitch black. Okay, so what is an advantage of using a properly mounted 5/8 wavelength antenna for VHF or UHF mobile services? This one, it would take me longer to explain to you why it has a lower radiation angle and has more gain than a quarter wavelength antenna to really give you a full qualified answer. And we don't have the time for that. So you may end up You may end up just having to memorize that answer. But what you really can remember is just 5/8 is bigger than a 1/4 inch, right? 5/8 of an inch is just a little bit over a 1/2 an inch, and a 1/4 inch is, well, it's 1/2 of a 1/2 inch. So 5/8 is going to be better. It's going to have more gain. The radiation is going to, signal's going to be, the radiating signal is going to be lower. So no matter what angle your signal is radiated, you're likely to encounter some reflected signals. It's going to bounce off of buildings. You remember that knife edge that we talked about? Sometimes bouncing off of a building can help you. If you're in downtown Atlanta and you know exactly where the repeater is that you want to use, say you're in a hotel room and there's a tall building in front of you, the signal that bounces off of the buildings next to that one blocking your view could give you a good enough angle that you still hit that repeater around the building that is blocking you directly. Okay. So give that a little bit of read. But why is it important to have low SWRs, which is standing wave ratio, when using coaxial cable feed line? So you remember we talked about was SWRs is the reflected power. So if your radio is 50 watts and you're transmitting 50 watts, the resistance along that coax, and all coax has resistance, all of them. There is no such thing as resistance-free coax. The surface tension on coax, on the electrode in the middle itself, is going to provide some resistance. Just like water, you go swimming, the water is resisting you a little bit. You may glide through the water, but there's still a certain amount of resistance. So an SWR is a measurement of the reflected power back to you. That means the amount of power that did not leave the end of the antenna. Well, the power that didn't leave the end of the antenna but was transmitted from your radio is lost, right? You intended 50 watts to go out, 20 watts gets reflected back to your radio, and only 30 watts are getting out. Well, you have a signal loss of 30 watts, right? So the idea is you want a low SWR. Now, that's where the type of coax that you use comes into play, okay? And you get, to be honest with you, in ham radio, you get what you pay for. I don't hate on Baofeng, but understand it's a $35 radio, all right? Everybody remember the Yugos? You remember the Yugo cars? You could buy one for like $4,000, brand new off the lot, right? How many Yugos do you see out there today? So you get what you pay for. You buy better feed line, coax, you're going to get a better performance out of it. Okay.
This is Alpha Tango 55 in Colorado. My Windows 10 machine just did an automatic update without my knowledge.
Hold on for a second.
I lost my signal link for data. I know there's a fix for that, but
sorry about that. Amron Zello. So the highest number, a higher number indicates that something's not matched. If there was a perfect match, almost all radios today are at 50 ohms. If the antenna is set at 52 ohms, it has an impedance of 52 ohms at a certain frequency. There's a mismatch there, very slight. The number might not be that bad, the SWRs, but if your antenna has an impedance of 75 ohms and your radio is always putting out 50 ohms, almost all radios are 50 ohms. There's not very many that don't. It's an industry standard. Antennas, you can build one, you can make them out of different materials, of different antennas, things like that do different things. You may have one antenna that is meant to broadcast on, 5 different bands. Well, if you remember, we talked about impedance is contingent on frequency. So you have an antenna that's out of a certain length. On 10 meter at 30 megahertz, it may give you an SW reading of one number, say 1 to 2, but then you go up to 40 meter and you may get 1 to 8. The impedance, because the impedance may have rose to 62 ohms. Okay. Typically, the lower number of very good SWR is 1 to 1. So typically, we say that a SWR lower than 1.5 is good. You should be really concerned if FWR rises any more than 2 to 1. If it's 2 to 1, that doesn't necessarily mean that your radio is putting out 50 ohms impedance and the antenna is 100, right? 2 to 1, double, or 25 ohms. That's not exactly what that means. But you know, if it's 2 to 1, you've got some you've got a mismatch, and you need to either tune the antenna with an automatic tuner, or you need to trim the antenna to bring down the SWRs. Okay. So, like I said, if you can understand that if we short out the end of the coax, that no energy will be put into the air. You know, also, if we leave the connector open and not completely tightened down on the antenna or the radio, the energy is not being transmitted fully across through the circuit. That's going to cause it to be reflected back to the radio, and and what that really equals is heat. It always equals heat. A radiated signal that can't go anywhere turns into heat. Electrical loads, it's the same thing. If you load up an antenna circuit and it has nowhere to go, just like electrical in your house, if it doesn't have anywhere to go, and there's nothing there to stabilize that load, it just keeps rising and rising and rising, and eventually it'll turn into heat, which turns into fire. So what is the impedance of most coax cables used in ham radio? 50 ohms. Okay, so that's the industry standard, is 50 ohms. Now, and you just have to memorize that is the standardized value that coax cable targets. However, coax cable, even from the factory, they always measure it at 100 feet. Okay, they always give the impedance, and they always give the SWRs or the amount of loss at 100 feet length of coax. You may use 200 feet. So when you look at a chart for, LMR 400 at 145 megahertz, if it says 1.8, that means it has a loss of 1.8 decibels at 100 feet. If you're using a 200-foot application, well, you can expect 3.6. You can double that. Why is coaxial cable the most common feed line selected for amateur radio antenna systems? One, coax is very easy to work with. It's flexible. It has a plastic sheathing or a rubber sheathing around it, so it's in a perfect state, or from the factory, it's waterproof. The only thing that's going to change that is UV rays from the sun that weathers that coax and eventually cracks the rubber, like anything rubber. But there's very few installation considerations that you have to make. Very few. So what I've done here is I've given you different types. We have ladder line. Ladder line is considered balanced line, but it typically it's going to come in 450 ohms. Well, if your radio is putting out 50 ohms, yeah, there is a multiple there from 50 ohms to 450, just like 600. There's a multiple there, a multiplier. So this is a line that can be used. It just needs to be tuned. Then we have what we call twin lead. Twin lead is 300 ohms. Again, there's a 50 ohm multiplier there. If 50 will go into 300 6 times, right? But what you've probably seen with feed line is there's little windows, little spaces here that are cut out of the plastic. Twin lead was very common with television antennas for the longest time. It was a flat ribbon, and on each side edge of that ribbon was a wire, and that was always considered twin lead. Really was used in TV antennas, and that's how you can remember that. And then coax for one, none of these have any shielding to them, none. Okay, but coax does. We have a copper braid or an aluminum braid. Sometimes there's a foil. There's foil that wrap the insulator, and the insulator is made out of polyethylene, so plastic or foam. And then they wrap the polyethylene with a foil. Some of the coax does, and then they may even double on that and use a copper braid. And the whole idea is this signal right here, this electrode right here, the conductor, that's where the heart of the signal transmits. It transmits along the surface of this. The more surface area, the less loss you're going to have. And you know, if you have stranded, some of these center conductors can be stranded wire, or they can be a solid core wire. So I wanted to show you the difference. These are the 3 different types of coax. RG58 you may be familiar with if you have cable TV. RG58 is what is used in cable TV. Or they use RG6, but you get the idea. It's so close. There's not really a whole lot of concern about loss because of the frequencies that are pulling through that wire. RG8X is the most common wire. However, RG8X does not work very well on 2 meter or 6 meter or 440 or 70 centimeter. It doesn't work very well on the higher frequencies. RG8X works a lot better between 3 megahertz and 30 megahertz. LMR 400, on the other hand, you can see you've got 2 shields here. This cable here is what I use. It doesn't bend very well. And when you have to watch it with LMR 400, you can't have a lot of sharp angles when you use it, because when you bend it, it changes the impedance of the wire. It squishes this polyethylene insulator here and presses the shielding closer to the conductor. And at 145 megahertz or 440, it makes a difference. And that's the give. If you were to have each one of these, one RG58 bends so easily, it's flimsy in your hand. 8X is very close to RG58, but you can see the conductors here are obviously a little bit thicker. Okay, and you can look how thin the insulator is compared to RG8X. LMR 400 is great because it's shielded so well. However, here's the difference. You can buy RG58 for about 20 cents a foot. RG8X is going to cost you about 35 cents a foot. It could be up to 50 cents a foot. LMR 400 could cost you anywhere from 75 cents to $1.25 per foot. So 100 feet of LMR 500 could cost you 125 bucks. The same 100 feet of RG8X may cost you only 35, 40 bucks. And RG58, hell, you can buy 100 feet of it at Lowe's for like 20 bucks, 15 bucks, 18 bucks, 100 feet of it, probably less than that. Okay. What is a major function of an antenna tuner? Well, I hope that we've talked enough about an antenna tuner that you know that it helps match the impedance between what the radio is transmitting and what the antenna is holding and what its characteristic is. Okay, if the radio is putting out 50, you really need the antenna tuner goes in between the radio and the antenna. what it does is it fakes the system. And one of the things that it does well is it lowers the power. Okay, so if you have high SWRs and you go tune the circuit, you may think your radio is putting out 100 watts, but it may only be putting out 80 if the SWRs are high enough and there is a high enough mismatch. So the best transfer of power is when the entire system has the same impedance. Impedance is quite like resistance, and a lot of people get them confused. However, resistance stays constant. It doesn't matter. It doesn't really matter about the frequency that goes across it. A wire at 100 feet is going to have the same resistance no matter what frequency you broadcast on it. Okay? Impedance changes according to the frequency. It can rise sharply, really sharply on a higher frequency. And sometimes it may be a lower frequency. Okay? Going back to this example here, if I were to use 8X to transmit on, what I should be using 8X for is 3 to 30 megahertz, and I go use it for 145 megahertz or 440, I'm going to have a lot of loss. I'm going to have a lot of reflected power come back to the radio. It doesn't burn up the radio. It won't burn up your radio. You'll just have some loss there. It's not enough loss to form enough heat to damage your radio. It just degrades your performance. So you remember we were talking about the power amp, the RF power amp that you can use. You can come out of your Baofeng's antenna port into the amp, go into it at 5 watts, and on the other side of the amp, you can come out at 40, 50 watts to an antenna. Well, if you're using the wrong kind of coax and you have loss and you don't have that power amp, 5 watts, honestly, you can literally go from 5 watts to 2 watts by using 8X. You really can. You really need to use our LMR 400 kind of cable. Okay? So it just simply matches these antennas impedance to that in which the transceiver is outputting. So remember, impedance is created by a combination of capacitors and inductors. All amateur radio systems that you go and buy is going to be 50 ohms. The antenna system in your Baofeng, 50 ohms. The antenna system in my 7308 HF rig is 50 ohms. Okay? It's really the feed line that changes the impedance. Impedance really, the feed line plays the most important factor. And that's why it's always important, that you have think of impedance or think of feed line like the transmission in your car. You don't want that thing going to the transmission shop, and you don't want it to take forever to get you to 60 miles an hour, especially when you're on an on-ramp to the highway, right? Well, in feed line, you want the very best that you can get. So it's okay to have a $5 radio and $100 worth of feed line. That's okay, because $100 worth of feed line, I'm talking where you didn't, it was worth that value, is going to allow that radio to perform with everything it has and not reduce any of its capabilities. So because impedance is a function of capacitance and inductance, a capacitor and or inductor can be used to change the impedance. And I show you the inside of what an automatic tuner looks like. And you remember, you see the coils of wire around an iron toroid? Those are your inductors. And these white things are your capacitors. Okay? And then these little silver cap things here are probably transformers. They can be transformers, they can be capacitors, they could be a number of things. It could be inductors as well. But really, an antenna tuner really is nothing more than a series of inductors and capacitors. And the way that the circuitry works in it is it uses both of those to kind of fool the system and come up with a match. So some operators even use long random lengths of wire. That would be me. I use random lengths of wire antenna, but I use an antenna tuner to match the impedance. Without it, I wouldn't receive a signal very well, and I wouldn't be able to transmit one very well. In general, what happens as the frequency of a signal passing through coaxial cable is increased? So you remember, when typically in radio, the higher the frequency, the more loss you have. Okay? So coaxial wire, again, that LMR 400, you're going to have a lot more losses at 440 megahertz UHF 70 centimeter than you would at 145 megahertz or 2 meter. You're going to have a lot more loss. So there's losses in wires, whether, no matter what wire you use, you're always going to have a certain amount of loss. Some is very minimal, and some is really great. Okay, so the coax has its own inductance properties along that center conductor wire, as well as the shield that is around the coax inside that rubber casing or plastic casing. And you have that little foam or polyethylene insulator, because that distance between the shield and the conductor provides the capacitance. If you remember the schematic symbol for a capacitor, it looks like two plates with air in between. That's the idea here behind this. So as the frequency increases, the reactance of the inductance increases, and is in series with the transmitter and the load, which reduces the current that can flow. Okay, moving on. That's more than you probably wanted to know. I get it. I feel you. But here's a real simple example to help illustrate this. When you go shopping, the doorway that lets people exit the building easily. If more people are going through that door like Black Friday, people are going to be piled on top of each other. Okay? Some people are going to get pushed out of the way. Some people are going to get pushed back outside, reflected back outside. If that doorway is not big enough for the number of people, the frequency of people coming into the building, going across the wire, so things can slow down, and not as many people, not as much signal is passing through, right? So that'll help you remember that. Which of the following connectors is most suitable for frequencies above 400 megahertz? It's real easy to see any of these. Okay. Now, there's two answers here that can really throw you off. Okay. A DB25 connector. A DB25 was basically a printer cable. It was 25 pins on the end. You remember the old printer cables that were pretty thick, and when you look down the end of them, you had pins? That's where DB25 comes in. RS213 is your serial port. It usually had like 8 pins on it. The older laptops had them, and it was a barrel connector. It was round. It reminded you a lot of an oversized mouse port. Okay, almost all computers made today don't use that 213 anymore. They're all made with USB. USB is the standard for peripheral connections. So the only two that are left here is A and B. Now they're talking frequencies above 400 megahertz. Okay, well, UHF, if you remember, UHF is 400 megahertz. Okay. However, the reason why they're asking you the reason why they're using an N connector is because a 239 connector, once you start hitting 400 megahertz, you start experiencing some signal loss. It doesn't perform quite as well. Whereas the N connector, this is what one looks like, the female and the male. it will go into the microwave range up into gigahertz without experiencing losses, okay? So if it helps you, it's the only answer that doesn't have a number in it. That isn't of much help, but I kind of noticed that it's the only one that doesn't have any numbers in it. The thing about this end connector is also, because look at this. This sleeve here goes up inside, and this little electrical wire goes into this little outlet conduit here, and then this screws on top of it. An end connector has very good water resistance. Water can still get in, but not nearly as much as it does with a 239. And I'll show you what a 239 connector looks like. So which of the following is true of PL259 type coax connectors? Well, first of all, any radio that you buy, almost all of them are going to have a 239 connector on the back. And this is what it looks like. We've all seen this kind of outlet, right? Well, you'll see two different types. You'll see a PL259 and an SO239. The difference is that SO239, they're both the same connector. Just the 239 is the female ends, and 259 is the UHF. I don't know why they do that, why it just can't be 259M and 259F. I don't know why, but it just is what it is. These aren't watertight because, as you can see, all you have is the threads here. And if you don't have it tightened down, that means these threads are loose. Water can certainly work into the valleys of this thread, and this connector is backed off just a little bit, and the water can get inside these marks here and slowly hit this conductor here. So that's why these aren't quite as good for water integrity. Why should coax connectors exposed to the weather be sealed against water intrusion? So when you have water intrusion, as you know, electrical current does not like water. What water does is it impedes the current and it creates heat. And that's why with enough water, you can create a fire. Okay. But in ham radio, when water gets into a feed line, it can blow your radio. It can cause all of the signal to come back to the radio. And when the radio is designed to send out 50 watts, and it's not designed to have 50 watts come in, yeah, you can fry some circuits with water intrusion pretty quick. It really all depends on how much water gets in it. If the water just gets along the shield, you're probably just going to have some signal loss. Okay, but heat is still getting created, and what it does is it ends up cooking that polyethylene sleeve in there, and eventually it'll burn a hole in it, and then water will continue down into the conductor, and then you have problems. Then you start seeing your signal getting fully reflected back to the radio. And we don't go out and check our feed line every day, so you know, it's not something you'd have to make a regular practice. But I always say, at least before and after every season, just eyeball your line. Just put an eyeball on it and see if you see any cracks or something like that. Just remember, it's just like your car. The least amount of time that you inspect, that you check your oil, that you check your air pressure and your tires, the least amount of inspection you do, the more problems you can expect to get. Okay? So this is an example that I was talking about, how the heat gets created because of a crack like this, and it ends up cooking and creating heat, and that heat is going to boil that sleeve to where eventually it's just going to blow out the line, and you're just going to hear a poof. When this happens, that's catastrophic failure, you stand a good chance of losing your radio. Not always, but it's a good chance, exponentially, that you could. Okay? But the first sign, hopefully, that you'll get is if you're on your radio in your house on a mobile and you go to transmit and you take the same route to work every day, and you talk to Tom or Dick who take their same route to work every day, and yesterday he sounded great, but today he doesn't sound as good. Did it rain last night? Did it rain on his end of town? You know, that's probably a good telltale sign that you need to just eyeball your the feed line that is exposed. Or even when it comes into the car, if it comes through a door crevice, has that door been open and closed so much that it is now worn into the feed line? Check those things and replace it if needed. What can cause erratic changes in SWR readings? One of the main things is if you are testing your feed line and you unscrew from the back of your radio and you screw into an antenna analyzer, if you sit here and you get an SWR reading and the meter is bouncing, you've got it on one frequency and the number is fluctuating right before your eyes, that is a telltale sign that you have a loose connection. It may be on the other end of your feed line as it screws into the antenna. But typically it's a real tell sign, because what happens is when the radio gets bumped or vibrated, especially if it's outside, the wind moves that antenna a little bit, it's going to move that loose connector, and it's going to change your SWR reading. So if you ever get and SWR meters can cost a few bucks, and they can cost a couple hundred. If you put it on there and you see the needle or the number fluctuating right before your eyes and it's not sitting still, that's a telltale sign you need to check your connections, okay? What is the electrical difference between RG58 and RG8 coaxial cable? So, because RG8 has a thicker conductor, it has less loss at a given frequency. So if you were to take RG58 and you were to test the SWRs on 145 megahertz, the reading for SWRs would be much higher than they are on RG8X or RG8 cable. And here's the difference. Look at the difference in the thickness. A thickness of the cable, there isn't a whole lot, but look at how much shielding you get compared to RG58. Look how much thicker the insulator is. That increases the distance and the capacitance between the shield and the conductor. Look at the one over here for RG58. It's just it's thin. All right. And then, there could be a lot more surface area when you consider all the strands in this. It's probably a lot more surface area to this RG8 than there is. So again, but both of these cables at 100 feet should have a 50 ohm impedance. But remember, because of the shielding and having more shielding, this RG8X is going to be slightly less flexible. It's going to be a little bit stiffer, but not by much. I can tell you that if I gave you RG8 cable and I gave you RG58 and you held them side by side, you may not immediately be able to tell the difference if you don't know what to look for. Okay? So the larger the cable means less loss. General rule. Which of the following types of feed line has the lowest loss at VHF and UHF? We talked about this. The best coax that you can buy, it's a little bit of a trick question, but is air insulated feed line. Air typically is a very good insulator. Okay? The farther the two metal surfaces are far from apart from each other, the less ability that the current has from jumping from one surface to the next. And also because typically air insulated line is really thick. It's not very flexible, not very flexible at all. And here's that. You remember I showed you a picture of it. This is the air insulated. It's got a little plastic spacer that goes spiral down the coax, and that keeps the shield from coming in contact with the conductor. And they can be all different types of material. These all are different grades. By the way, this is called Heliax. Heliax feed line is an air insulated line. To give you a little bit of a realization, Heliax can cost you more than $5 a foot. $5 a foot versus $1.25 of LMR 400. So most ham radio guys don't use this wire. It's just not, you know, would you pay $500 for 100 feet of this line? $500, that's a radio. You know, some people do, but it's not very common. Where you see this being used a lot is on high repeaters. I'm talking like towers that are not repeaters that are on top of a mountain, but I'm talking repeaters that are 1,500 feet tall. They're on top of a television tower. That's 1,500 feet of feed line that it has to use. You bet that feed line to prevent loss at 500. You imagine if I have a repeater close by to here that's 1,500 feet tall. It's at the top of a television tower. That means the antenna is somewhere along that 1,500 feet. If that's at 1,000 feet, you need 1,000 feet of feed line to go from the antenna down to the repeater, the box that has the two radios, the duplexer that I showed you earlier, the brain of the repeater. You better have some really good feed line or you're going to experience a lot of losses. At 1,500, at 1,000 feet, remember I told you repeaters are about 30 watts, 35, 40 watts. That's all they transmit. How much loss do you think you could expect 1,000 feet of feed line to give when you're transmitting at 30 watts? If you're using poor feed line, it's realistic that you may lose over half of your power and only transmit 20 watts instead of 40. Okay. That's the end of sub-element 9. We're going to go ahead and hit on 10. Let me get that one up real quick. Okay, and we'll bring it back up here. And we're going to get into sub-element 10. Sub-element 10, you have 2 questions from this that covers antennas and feed line. We've already kind of gotten into a little bit. It's 10 o'clock. If you need to leave, that's fine, but I'm hoping that I only need an hour to finish this. So I'm going to probably go to about 11. But you're welcome to stand by, ask questions you need to. So let's jump right into sub-element 10. They call it T0, but it's 10. Which of the following is a safety hazard of a 12-volt storage battery? So when we look at all of these choices here, batteries don't really have an RF emission quality to them of any nominal amount. I've got batteries, dry cell batteries, or deep cycle batteries that are literally 2 feet from my radio underneath the desk on standby for emergency power. They've been there, since the radio's been there, and it has absolutely no effect. So radio frequency emissions isn't the answer. And because it isn't, all these can't be the answer. So we're left with 2 of them, okay? So shorting the terminals on a 12-volt storage battery with a good conductor can result in a very high current flow. And you can remember the whole thumb exercise that we use with the pi, P-I-E. If you cover up the P, which is on top, I and E are side by side, you would multiply them. Okay, John, so it says 3 questions. You may be right. I'm not going to disagree with you. I may have just been kind of hurrying. But anyways, so if you can get the current and the power, the current and the resistance, Or if one of these, if you have a high current, it's going to mean high power. So it can, and what that can do is it can cause burns, fire, and it can even explode the battery. And I'll show you a picture here very shortly. By the way, John, it's good to see you. You've been quiet tonight, but it's good to see you. What health hazard is presented by electrical current flowing through the body? So what happens with electrical current if you touch a high voltage line? Well, what it does is it cooks your organs, and it cooks you from the inside out. That's why, don't mean to be graphic, but electric chair, typically somebody's going to be smoking from their ears. They're going to be smoking from their mouth because the inside of them is cooking, and it might not be so evident. I've seen a man die from electrocution, and all he did, it looked like he was having a little bit of a seizure. It really did. We didn't know that he was digging and had hit a power line. We were laying fiber optic, and it wasn't until we started smelling his hair melt that we knew that he was on contact with a live line. So, and what it does is, if you can remember that your cells, your body has an electrical current in it, and different organs produce certain different currents. So when you have an electrical path through your body, and then you introduce a high voltage signal to it, you're going to disrupt the cells in your organs. They're going to cause them to congeal, to bind together, and they'll start cooking and creating heat. And because of that, what it can do, it can start causing your muscles. And typically, just for you to know if it's all answers are correct, if you can verify that 2 of them are right, then you know that all of these choices are correct, is the right answer, right? If you're sure that 2 of them are and the third one isn't, well, you can't pick 2 answers. You're unsure about the third one. A good bet is that all these choices are correct. So your nervous system, again, it functions using electrical signals. Your brain is nothing but electrical signals. It sends signals to your organs, down through your nerves. And that's why when you touch things, you get shocked as well. So, and so because it uses electrical impulses to move your fingers and move your arms and your eyelids, any kind of electricity that's introduced to your body can disrupt that cell function. And, your body also acts as a resistor. So because it's a resistor, an electrical current introduced to your body is throughout your body is going to distribute heat. It's going to dissipate the heat that the electric is called, but it's got to go somewhere, and it stays in your body and just starts cooking you. So as the current increases, the heat dissipated also increases, and that heat dissipation equals transfer to your body. And your body starts stacking up that current and creates heat and starts cooking. And that's why you've heard people, in the electric chair, their hair will burst into flames, stuff like that. I won't get too graphic about it. But in the United States, what is connected to the green wire and a 3-wire electrical AC plug? So the best way I always remember, because sometimes you get a white, a black, and a red, and it's hard to tell which one is the ground. Okay? Sometimes you luck out and you get a green one. And green, I personally equate green to grass. And I equate grass to earth. And earth ground. Ground can be called earth ground. So that's how I make that association, is the green wire equals grass, which equals earth. So again, a standard electrical cable usually contains 3 wires. Most of the time, it's going to have the black wire, which is your hot. The wire is the return or your common. And the third wire usually is going to be a safety ground. It'll either be bare or it'll be green. If there's a green wire, again, the association, green, grass, earth. And the reason why it's uninsulated is because current does not flow through the ground. Okay? You can touch a ground all day long and it's not going to shock you. Now, if you go touch the hot in the ground, you've now created a loop, and you've made a connection between the ground and the hot, and your body is the bridge. Well, you can probably guess the results. Okay, and the whole idea of a ground anyways is to prevent shocks. So if you need again, if you need a last second reminder, just remember that green grass usually means ground earth. Okay. What is the purpose of a fuse in an electrical circuit? Well, you remember we talked about this back in a few lessons ago, and basically a fuse is just simply there. A circuit has been rated to carry a certain amount of amperage. And if there's nothing to throttle that, the amperage could climb and climb and climb, and it just creates heat, and then you'll have an explosion. You'll have fire. What the fuse does is, if a circuit's been rated at 30 amps, you put a 30 amp fuse in it. And once it rises above 30, well, that fuse is going to blow, and it's a safety device. And the little wire here, whoops. The little wire here in the middle will snap, and you can see that the wire doesn't continue. Just like inside of here, you see these little arced wires. The higher the amperage, the thicker these wires are. So this green one has a really, really thick wire, but this orange one is almost, you can't see it. I'm willing to bet orange is 5 amp and green is 30. These are color-coded. Richard, you might know. But they're color-coded, and I don't remember the actual values of the numbers. But a red fuse is always going to be a certain amperage. Green is always going to be a certain. But the best way that I know is I look at the end, and then I can look at the wire and see the thicker the wire, the more capable it is of handling more amperage. Okay? And a fuse is designed to vaporize this little small wire if the current becomes too large. And it basically just creates an open circuit. So it's always put in on the hot wire. Some folks in ham radio, they put one on the ground and on the. It's not necessary, but you can never be too cautious with ground. There's no such thing as too much ground. Ground is always a good thing. Why is it unwise to install a 30 amp fuse and place it with a 5 amp fuse? Well, let's think about this. If a circuit was determined to need a 20 amp fuse, it means when the current rises above 20, it's going to blow it. Okay? If the circuit is designed to be a 5 amp circuit, anything above 5 amps, it's going to blow it. Well, if it's that 5 amp circuit no longer has a 5 amp fuse as a safety, and you put a 20 in there, that current is going to keep building until it hits above 20, and then that fuse will blow. Well, the difference between 20 amps and 5 amps in that fuse could result in catastrophic failure, which means excessive current that creates heat, which then when the heat has nowhere to go, it just heats up, and it starts melting things. It starts melting the component, the metal, or start melting the plastic insulators. Usually it'll melt the sheathing in the insulator, and it'll cause a fire. So again, fuses are selected for a circuit based on the amount of current, the amperage that the circuit has been rated for. You don't want to use a bigger fuse. And if you use a lower fuse, if it's a 20 amp circuit and you use a 5 amp fuse, well, you're just going to eat through fuses, right? Because If that circuit, it normally typically has 11 amps on it, but it has a 20 amp fuse because they've given that circuit a little bit of leeway, and you put a 5 amp fuse in there, but the normal load or current going through it is 11, you're just going to chew through fuses. So you really want to use the fuse to match the capability. So rather, I don't know if you remember in a physics class, where they use a 12 gauge copper and they connect it across the terminals of a 12 volt battery, and the wire starts glowing. That's excessive current for 12 gauge wire isn't able to handle 12 volts. And a car battery can have several hundred amps. It may be 12 volts, but it could be several hundred amps. We're talking 500, 600, 700 amps. You put a 12 gauge wire across that, you're going to melt that wire. You're going to cook it. And the best way, to give you an example of a car battery, when you go to buy a car battery, they've asked you, well, how many cold cranking amps does it have? So car batteries are rated, they're all 12 volt, but they rate them on the amperage load that they can accept. So a Ford Super Duty 350 Super Duty is going to require a lot of amperage compared to a Toyota, a Toyota Corolla. What is a good way to guard against electrical shock at your station? Well, first of all, three wire cords are, you have your 3 wires, and one of those is the ground, right? You have your flat spade electrode sticking out, and then you have the round one, the round peg there. That's your ground. So you are using the ground of the house to help ground your radio, the electrical components in the radio. The reason why you need a grounding on the antenna, and why you still have to use ground rods and use it on because you could get your antenna basically as a lightning rod, and a lightning strike is measured in joules, Joules, I think, and it could be tens of thousands of joules, hundreds of thousands of volts. That'll fry anything. There aren't a whole lot of things in terms of electrical that can handle and absorb a lightning strike. Usually there's going to be a fusible link in there that trips the circuit. Now, it may not blow it permanently. You might be able to reset that fusible link, but so connect all AC power station equipment to a common safety ground. That is one of the most common ways. Almost every radio out there that you buy is going to have 3 prongs on it. I can't remember last time I saw a 2-prong radio, power cord. And also, when you plug the radio in, use a surge protector. Okay? I mean, a surge protector is probably plugged into a wall, but the surge protector is specifically there. There is a trippable circuit in there that when a surge happens, even if it were to hit the telephone pole and send a surge into your house, that surge protector trips the circuit and it cuts it opens the circuit before that surge can make its way up the power cord to sensitive equipment. So a key to avoiding electrical shock is you use properly connected electrical wires and good safety grounds. Your 3-wire grounds are the best. And you also want to avoid ground loops. And I'm going to show you what that means. So a GFI protector is a very good, in fact, building code now says that you have to have these in the bathroom and you have to have one in the kitchen, I believe. And you have a test button, you have a reset. I have clippers that I use to trim beard mustache, and I don't know why, but it keeps tripping my GFI circuit. I really don't give it a whole lot of attention because the GFI circuit is doing its job. It's probably something wrong with my clippers, and I really should discard them and get a new pair, but it's always done it. So it trips the circuit, and I just push the reset button, and it works fine. So a GFI ground fault interrupter will sense cases where the current is flowing in the ground and disconnect the power. So if you were to drop a radio in your bathtub, the idea is that water is going to travel along all the wires, and it senses that ground wire carrying a current, and it opens the circuit by tripping. Which of these precautions should be taken when installing devices for lightning protection in a coaxial feed line? So mount all of your so basically what you want to do is you want to have either a copper pipe or you want to have a copper plate, and you run an individual line from each component. You run it to that plate or that rod, and some people just use hose clamps. You want it to have contact with that plate or that pipe, and then you have bare wire, usually 4-gauge wire. It goes outside and is clamped to a ground rod. And a real good ham radio station is going to have multiple ground rods, 2 or 3 at least. You want as much grounding as possible. Remember, lightning always travels the path of least resistance. Okay? So I give you an example here. Now what you're seeing here, you've got the plate. And why you're seeing these wires hanging down is because, remember, typically ground isn't going to have a current on it, so you're not hurting anything by these wires being here. But what he's done is he's basically connected them already to the plate, so that all you have to do is just from above here, just grab one, pull it out, and connect it to your radio. And what he's probably doing is he's taking a picture along the way, but he can put one on. It looks like there's a dummy load. It looks like a tuner, and it looks like maybe another radio. That may be his power supply. It looks like maybe a regulated power supply. And all those you would put on this one plate. And then you see this bare wire here. This bare wire is going down into the floor, or it's going out a window, and it's going to a ground rod right below this station. Ground rod usually is an 8-foot copper-clad steel rod. It's steel in the core, but it has a thick copper cladding around it. Typically with grounding, you want it to be of all the same metal type. It's not the worst thing if you don't, but when two metals of different substance, so aluminum and copper, lead and copper, steel and copper, and there's an electrical current going between the two surfaces, what happens is what is called electrolysis. And electrolysis can create corrosion. So it's one of the things that it can do. So you really want to use, and since you're already using copper probably most likely in your power lines, chances are you want to use copper for your ground lines. And then because you're using bare copper wire, solid core copper, to go to the ground rod, you want your ground rod to be copper as well. Just remember, it's always good to remain copper. Okay, copper is one of the best conductors of current. And that's why you see it in your house. One of the only better ones than that is silver. Do you imagine how expensive silver wire would be? So the next best conductor, and is a lot cheaper, is copper, hence why you've seen it used. Aluminum is below that. So if you ever see aluminum wiring, aluminum contacts, it's a cost-cutting measure. It's by no means performance, designed for performance. It's purely a cost-cutting measure, or the manufacturer to cut down on costs, or the builder. You can buy aluminum wire a lot cheaper than copper wire, and a lot of building codes won't let you use aluminum wire. Aluminum conducts heat differently. It dissipates heat differently. and it behaves differently than copper. So, little bit graphical point. Each one you want to bring a ground wire off of it, connect it to a single point, and then only one wire coming from it to your ground rod. Okay? You do not want a ground loop. And what a ground loop is you're doing what the difference here is when you run a ground wire not only to the common point, but you run them from component to component. Okay? And that's the difference is you got this wire here, you got that wire there, this wire, and this one. Don't ever connect your grounds from component to component. Always run them independently on their own leg, their own wire, to a common point, whether it be just a copper pipe or the copper plate like you saw. Copper pipe works great, and just hose clamps. However, remember, metals of likeness. Hose clamps are not made out of copper. Rarely are they ever made out of copper. Almost always they're made out of aluminum or steel. However, it's not a must-have. If you use metals of dissimilar, some people take rebar. If you know what rebar is, it's just a steel textured rod. You can use that as a ground rod. It's better than not having anything at all. But just remember that you could be, when water gets introduced to that, because that ground rod is in the ground, water, moisture, and then the wire is, that bare wire is going outside and is susceptible to the elements. When water's introduced to that and you have electrolysis, that's where you get an introduction to corrosion. It's very slow, very gradual, but it's one of those things, if you know you're using dissimilar metals, put that into your inspection of your feed line. Just check that out and put your eyes on it. Make sure that you don't see any white crust or a light green crust developing along the wire. If you do, sandpaper it off. Okay? The idea is you don't want to create a ground loop. Everything else here is fine. You just don't want to connect the component to component. Okay? So what safety equipment should always be included in home-built equipment that is powered from 120 volts? Well, I like to think that this is really a gimme, because a voltmeter is just going to give you a reading. It doesn't provide butt kiss for nothing for safety, nothing. It just allows you to get a reading. Now, we talked about inductors in parallel. We talked about capacitors in series. You might be led to believe that those could be safety devices, but remember, an inductor stores electricity from it stores energy from a magnetic field. A capacitor stores energy from an electrical field. Those don't really sound like safety devices to me. The whole idea of an optimal safety device is that the circuit breaks and it opens the circuit and creates the current from traveling any further. So what I've done here is I've shown you typically what it's going to look like. See the fuse here that's on that hot lead? There's a fuse. And this is the common block that he is using. It can be as simple as this. It just has to be a common point. And as you can see here, he's got a ground cable, short and sweet, running to the back of this block. Now, these other pieces of equipment on either side, he probably needs to run those as well. But what you see here is, as well as, do you see two? These look like fuses, right? They use these kind of fuses over here, what we call blade fuses. And that's fine too. There's a number of them you can use, just as long as you put one in. But they have one on the black and on the red wire. I took a picture of this rig runner because that's what I use. In the back of my Go boxes, I use rig runners. It's basically a fuse block. And these are called Anderson power poles. Very popular in ham radio. They're lifesavers because you can connect very easily to them and disconnect very easily, very fast. If you have a mobile radio that you want to take inside and take out to your car, I always suggest running power wire through your firewall up to your battery, and then on the interior of that wire, put Anderson power poles. And then your radio, the power lead from your radio, put them on there as well. Okay? So what you're seeing here is Anderson power poles. These are your fuses, but these are your Anderson power poles. Okay? And what he's done is, let me see if I can. This is an Anderson power pole. These are Anderson power poles. You will hear a lot about them. I cannot say enough higher recommendation to use power poles when you are setting up a station. The only problem with them is that they tend to have, you need a special crimper for them. But I will tell you this, if you join your local radio club, not only do you have a fountain of knowledge to glean from, but as well as you have a lot of ham folks in that club that have all this equipment. They have the antenna analyzer, they have a crimper, they have Anderson power, they have everything. And they can teach you, show you, or let you borrow their, or they'll come over and help you with their equipment. Okay? And I like this rig runner because it uses these right here. It uses just regular blade fuses. I keep a box of these in my car always. So, and usually when you buy a box of them, it has a little puller that comes with them to help you reach the side of these and pull them. But I can easily replace these because my car has them. So I prefer to use the blade type. Does the same job as a barrel type, all of the other types. These are just so much more common. And again, if you own a car, you own these fuses. You should. What should be done to all external ground rods or earth connections? You bond them together with heavy wire or conductive strap. So what we're talking about here is we're talking about, I see you, Doris, just a second here. So what I see here is you see these straps, and what they've done is they have bonded. These are bonding points. Bonding, and bonding. And what they're doing is what they're telling you is to bond all of your leads to one place. Okay. The heavy wire or conductive strap is to make them useful for high current situations. Heavy wire has more surface area to it, and a conductive strap, these straps have more surface area to them along the sides of these than a heavy wire would. Okay. So Doris, you're asking what amperage. So as you can see, your radios will tell you what amperage you should use. Most of, like mine, this has a 40 on it. That's my whole radio, my whole block. The max that it will hold is 40 amps. So I can only have 40 amps worth of wires here. So a lot of mine are 15s. Okay. And I've got a few. So like I have a red LED light that I use for night ops, because red light, the cones in your eyes adjust to red light the best. I have a tactical light in my box that is just red, so that when I'm doing radio ops, if I have to switch to a firearm, and Scout, my eyes are already adjusted. They're not overpowered by a white light in a tent somewhere, as well as red light can't be seen as far as white light can. So my point is that I would probably put that one, because it's LED, I'd probably put that on a 1 amp or a 5 amp fuse. So it just depends on what you're going to connect to it. Oh, I'm sorry. The reason why this one has a 40 is because it is the current coming in. So if you look at these, you got 50, 66 amps here. Well, that's fine. Just because you have a 25 amp fuse in the circuit doesn't mean it's always going to have 25 amps across the circuit. That's just a maximum that it can handle. Most radios are 25 amp. Most radios are 20 to 25 amp. That's a good fuse to put into your power of a radio. So what it's saying here is that I am only limiting 40 amps coming into this entire block anyway. So if it rises above 40, this is the one it's going to blow. If I have a surge come in from, you know, a wall outlet or my batteries, it's going to blow this one fuse and protect all the other components that are on this block. That's why I like this block, this rig runner, for that specific purpose. Okay. So grounds don't need to be waterproofed. They don't have to be taped. The only reason why you would do that is because, again, electrolysis can create oxidation, and any electrical current across a metal surface that is exposed to the elements, where you have rain and then heat and then sun and then cold, then water, then heat, you can expect oxidation to take place. Oxidation can kill a current. It can inhibit the transfer of current between two surfaces. With a thin layer of oxidation, it doesn't totally blight. If the oxidation is real bad, yeah, it could probably stifle it altogether. Okay, but you ever seen your car? You know, your car, you get, you've seen them clean the connectors and make them really nice and shiny. Well, not only are they taking the little white powder cake that tends to build up on your positive terminal, they clean it as well to get any oxidation out, to get a really good bare metal contact between two surfaces. And what we're talking about here in bonding is, again, 2 ground rods. You want them to be about 6 feet apart. They have to be 8 feet in the ground. A good length for ground rod is about 8 feet. Now, I've talked to an electrician in my area, and he told me I only needed a 3-foot ground rod. Well, I'm not going to believe him. He may be an electrician, but he's not going to replace my radios if they blow, and he's wrong. So I'm going to use 8-foot rods, and typically I use 3 of them, and I just daisy chain them together. And then I have a good solid ground. And again, copper clad ground rod, copper solid core line coming in from the plate or the pipe through the window or through the floorboards out the vent, clamped with copper clamps or copper cladded clamps to the ground rod, and then I'm joining them together with the same bare wire that I'm using to come to the ground rod from the station. What can happen if a lead acid storage battery is charged or discharged too quickly? Well, if it drains a current to a load too fast, or it gets charged too quickly and it loads up the battery, it can cause it to overheat. It can give off a gas from the acid inside of it. It can cook the acid and let off fumes, and or it could explode. Here are 2 batteries. These 2 right here have cooked. You see how they're bulging out? And these 2 batteries here are fine. They're perfectly normal. He's probably cooked these, and he's going to replace them with these. And these are deep cycle batteries. And what has happened is he's probably put them on a charging system, and these just experienced really fast charging, or they were discharged super fast. It takes time to charge things, and it should take time to discharge things, like your phone. Okay. When you talk on your phone for a couple hours, it's an oven, right? It's hot, and that's because there has been put a load on that in a short amount of time that's creating heat. And you've seen folks, cell phone batteries. We've all heard instances where the cell phone will explode in their pocket, or it explodes. There's a car fire on the side of the road because their phone was in the center console charging and it blew. Well, what that probably is from in the car is they're using a cheap gas station charge. I call them buttons, but the 12 volt goes in the cigarette lighter. They're buying really cheap ones, and what it's printed on the outside of it may not be what's on the inside. It's junk. So it's always important to buy good quality components, good electrical components. Don't always go for the lowest price. Remember, you get what you pay for. Almost always that's the case, right? So this is an example of cooked and normal battery. But here's what where it is bulged out, and if it's not, typically when you charge something, right, you plug it in and then you walk away. Well, the problem with these is if you put them out in your garage and you've got a faulty charging station, it keeps loading it up, and loading it up, and the circuitry inside the charging station does not sense 13.8 amps, and it just keeps loading that battery up. And as it does, it cooks it and causes it to bulge. And if it keeps doing it long enough, you have catastrophic failure where it just blows out the sides of the radio, and hot acid is going to spew in all directions. Okay, so this is the last stage. And I can see this is a dirty garage floor. If anybody's ever told you, always charge your batteries on a piece of wood, like a 1x8 or a 2x8. Don't set them on bare cement to charge them. So here is an example where they may have set it on the pavement, and this is one of the results of that. It could be. Okay. What kind of hazard might exist in a power supply when it is turned off and disconnected? Well, you could receive a shock, because remember, power supplies are a series of capacitors because it stores electrical energy, stores energy of an electrical field. It has some transformers in it because your radio is 12 volts because it's meant to go in your car, and your household outlet is 110. It needs a transformer to help step down that voltage from 110 coming out of the wall to 12 volts that will power your radio, or 13.8 volts to power your radio. So because of that, remember, capacitors store energy from an electrical field. Capacitors require time to drain. They just don't immediately, when they stop accepting a charge, they empty and they're dead. That's stored. It has to dissipate. That load that's inside that capacitor needs time to dissipate. So TVs have rather large capacitors in them, huge capacitors, and you can unplug a computer monitor or a TV. I'm talking the old TVs, not your LCD and your flat panels. I'm talking your CRT monitors, that have the tube in them. You go stick a screwdriver in that the next day, you could get killed. Those capacitors could very well still hold enough amperage and enough, because amps kill. Volts, remember, are just the force. The current, the amps, that's the killer. And those capacitors could store enough amps that it'll kill you. I'm A+ certified, meaning I can work on computer hardware years ago. One of the things that they taught us, that don't unplug a monitor, screw off the back, and just start sticking a screwdriver inside there, you're asking for trouble. What you need to do is drain the power from it first. I'm sorry, you need to drain the current that those capacitors are holding. Okay. And this is an example here. This is the inside of a tuner. Okay, or this could be it very well could be a power supply. But these two barrel connectors here, these two maroon and silver, those are capacitors. Power builds up into those, and then when it builds up, they're rated at a certain rating that it only allows a certain amount of current to leave them. And because of that, that power stays stored up in them. Again, it takes time for them to drain. Okay. And you'll get a good shot. Voltage, if you go touch your household outlet, typically is going to be 15 amps. Most of the time, it's going to be 15 amps. 110 is, and 110 volts. If you go and you stick a fork in that, it'll light you up. You'll know that you did it, but it's not going to kill you. 15 amps isn't enough to kill you, but 100 amps could. 200 amps will fry you. So you get the idea. So if there's enough of the large enough charge on a capacitor, you could become inadvertently a low resistance drain, meaning you could be the conduit that the power dissipating from these capacitors could drain into you. When should members of a tower work team wear a hard hat and safety glasses? Well, this is pretty, tower work is hazardous, right? And we've always kind of been, taught that you wear safety equipment throughout your exposure to hazards. Okay, you don't put them on for the first 5 minutes. You put them on through and keep them on throughout your exposure to that hazard, because accidents are just that, accidents. You never know when they're going to happen, and when they do, they're a surprise. So it only takes one time that you don't use safety equipment to cause permanent injury or death. So, the one guy that lost his leg, falling off of a tower, if you talk to him, he'll tell you, yeah, I was a dummy and I didn't think that rigging and strapping myself to the tower was important. And boy, did I pay a price. So whatever it takes, find your own motivation, but always stay safe. It's not worth it to your spouse and your children over a damn $300 radio, right? $300 isn't worth your kids going without a parent. $1,000 isn't. Okay? So the small inconvenience of a hat and glasses, it just isn't worth the risk that you get if something were to fall off that tower. Somebody's up 100 foot up a tower and they have a hammer and they're using it and it's sweaty, it's 100 degrees out, and that hammer slips out of their hand. Imagine a hammer falling 100 feet and hitting you on the top of the head. With a hard hat, it'll ring your bell. It may possibly even crack the helmet, but you're probably most likely the worst you're going to get is a headache and maybe a little neck pain, maybe. Or if they drop a connector at 100 feet and you're looking up at them trying to, keep an eye on them, your eyes are exposed, right? They're a direct line with whatever he drops. If you drop something from 100 feet, it ain't nothing to go through the little spongy material of your eyeball and go into your brain. I mean, really, think about it. So what is a good precaution to observe before climbing an antenna tower? So the first thing you want to do, you want to make sure your safety gear is sound. And if you're going to put on a climbing harness, so when I deer hunt and I'm in a climbing stand, I know my equipment. I've used it. Only I've used it. But each time I use it, I check the webbing, and make sure there's no frays, there's no tears, it hasn't rubbed against the tree with that strap that goes around the tree and then my harness clips to the strap. I make sure all those things are sound. And if it's frayed or fuzzy, I throw it out. It isn't worth it to me. My wife and my kids need me more. So just inspect your gear, okay? If your glasses are cracked, well, if something comes 100 feet down, isn't it when it hits those glasses, it's just gonna spread that crack, right? The glasses probably aren't going to work that well and do their job because the energy is not going to it's not going to dissipate across the whole lens. It's only going to go as far as the crack, and it's going to increase the crack. And if there's enough energy behind whatever hits you in those safety glasses, it'll keep going through the safety glasses. So make sure that your climbing harness is in good working order, that it's snug, it fits you properly. Don't, if you're little Speedy Gonzalez, don't use Bubba's climbing harness. If you're 120 pounds, don't use a 300-pound man's harness, okay? Because what's going to happen is when you fall, you're probably just going to slip right through the harness. The top of your body is a lot heavier than the bottom. As soon as you turn upside down, you're going to fall right out of that harness, and they're going to find you dead on the ground, and they're going to find the harness just swaying in the wind. Under what circumstances is it safe to climb a tower without a helper or observer? It's never a good time. Even when you climb a ladder to get on your roof, while you're on your roof, repairing a shingle or whatever, have your spouse out there just standing at the base of the ladder. Even if they're on their cell phone, you just need them out there, because if they don't hear the thump when you hit the ground, or they don't hear you caught up and dangling off the roof, and they're inside, you're probably going to be long gone before they wait a minute, he's been out on that roof for 2 hours. Where is he? It could be hours before it dawns on somebody that you're missing, and they go out, and if they've gotten to you in 5 minutes, called 911 and got you mobilized to the hospital within 20 minutes, you'd probably be living. But now that chain reaction starts at 2 hours, and you're probably cold laying on the ground, right? So never. You always want to have a buddy. Somebody. It can even be somebody that climbs with you. So here's Bubba right here, all 300 pounds of him. Don't use his harness. Okay? But he's got a climbing partner that's going to go up with him. And the reason why is because when you're handling equipment, it's a lot better for two people to handle it. If one person's handling it and it gets out of his hand, one of two things are going to happen. He's going to have to drop that equipment, or he's going to drop. With two people, you get a lot more stability on everything that you do. So just never climb it without somebody to help you, go up with you, or just be on the ground to observe. Again, if they're down the ground to observe and you fall off the tower and you land on the ground, it's within seconds that they're calling 911 and starting to activate that chain of reactions and getting that ambulance to you. It may be 10 minutes before that ambulance gets to you, and now the care has started. If nobody's out there and you fall off the tower, this dude falls, it could be 2 days from now before somebody goes to that site. You think you're going to survive falling 100 feet for 2 days? So always take the time to get someone to help you. Which of the following is an important safety precaution to observe when putting up an antenna tower? Really, the main concern, the ultimate concern, after you've taken care of the safety gear, is electrical wires. You do not want to erect a tower near electrical wires. The idea in mind is the safety thought is, you don't want that antenna to, if it were to fall due to weather, you don't want it to lay across the electrical lines. Coming with a force, with it being straight up and falling, by the time it lands on an electrical line, it's going to snap the line. Okay? Now that line's going to be laying on the ground, and the antenna, or your tower, is going to be sitting on top of a live electrical line. Now you can't touch the line until the power company comes out there and kills the power. And now you've put as many as thousands of people out of service. So, and if you do it, electrical companies, if they can see clear negligence on your part, they can charge you for the bill. They can charge you for the repair. It doesn't happen often, but it can happen if they know that you were grossly negligent and causing so many people to be without power. How would you feel if you killed the power and up the line from you was a hospital or a fire department, and somebody makes a call, or somebody, you know what I mean? Think about that. Like the chain of catastrophe that could happen. It just could be so monumental to such a small innocent mistake. So the grounded wrist strap answer, that's only to ground yourself to the equipment so you don't get what we call ESD, electrostatic discharge. You don't have that transfer. Insulating the base of a tower isn't going to do anything for lightning strikes. And it really kind of messes with the grounding system. Okay. An insulator, I mean, breaking a point in the tower where you use a conductive material like PVC between a space between the base and the tower itself. Because now the electrical current, a surge does not have the ability to travel completely down to the ground once it hits that insulator. It's cut it. And now what you've done, and now that current doesn't have anywhere to go, it's going to blow something between the tip of your antenna and where that insulation is. So again, you want to look and stay clear of all electrical wires. Here's a perfect example. I don't see any electrical lines over here. Look in the back. It was a smart move that he probably put that antenna here and he didn't put it in the back of the building. Okay. Yeah, it could have fallen and hit in the dumpster, knocked over the fence. It could have landed on the roof and damaged his roof. It could have landed across the road. But there's nothing there that causes it to be electrical. You could just simply move it out from the road. You can get it off of your roof, take a welder and cut it. But if it's on a live electrical line, you're sitting duck. You have to wait until that power's cut for you to do anything with your tower. So you just don't want it to rest. And this happens all the time, man. All the time with towers. John Jacob Schmidt, the head of Amron, he literally just a month or two ago, his tower did exactly this. It folded over. Now he can only use, so many feet going up to where that bend was. But the rest of it, he has to trash. What is the purpose of a gin pole? So what a gin pole does, let me give you a diagram here. A gin pole basically just, it straddles beside the antenna. And as you build it, there's a pulley at the top here. Let me get there's a pulley at the top here. Okay. And somebody grab this line, they pull on it and it hoists this up. Now you have somebody at the top climbing at the top here. The gin pole is carrying all of the weight. So all the guy has to do up here is just swing it around a little bit, set it in the pilot holes and put in the set screws and tighten them. He's not carrying any of the load. He's able to keep his footing. He's able to keep the golden rule 3 points at all times in contact with the tower. Okay. And gin poles can come in all different types. Some gin poles are only 10 foot long. Some of them you're talking, see, like this one right here. You see what he's doing here? The guy's using the rope. He's hoisting this top end of the tower up, and all this guy's got to do, he's strapped around safely around the tower. All he's got to do is just kind of wiggle the tower while the gin pole takes all the weight, set it in the holes of the section below it, and then put the set screws in. So that's all a gin pole is. It just helps lift materials up to the highest point while you're building a tower. Okay. What is the minimum safe distance from a power line to allow when installing an antenna? So, ultimately the golden rule is you want at minimum, the optimal, what you want is if your tower is 50 feet, you want to be 50 feet away from the antenna, from the power lines. And in fact, you want to be 60 feet because you want 10 feet plus. Because when it falls, it could fall with a little momentum that takes it sideways a couple of feet before it lands on the ground. Okay? And if you realize the arc of something falling, you're measuring from the base of your tower to the base of the telephone pole. That 10 feet allows for that arc as if the tower were to fall. So, however tall your tower is, plus 10 feet. Okay? You don't want it to come any distance within 10 feet of the power lines, as well as 10 feet is a good distance so that there is no electrical current that transfers between the power line and the tower. You know, your tower falls, you go out there in the middle of the night, you can't see it. If it's laying on a tree or if it's laying on a power line, it may not be sparking. You go out there and set your hand on it trying to move it out of the way, and now you're cooking. So you may not see the hazards until the morning daylight. Okay? So here's an example of a radio tower that a storm has caused it to collapse. Now, what they'll have to do is send somebody in here to cut it this high up, and then they can rebuild the antenna, get replacement parts, and rebuild it up higher. But when this falls over, you want the power lines. I see some back here in the distance. You want them to be more than 10 feet away from if it were to fall from the base. Okay, that isn't always practical. Sometimes you don't get that capability. But it's just a rule of thumb. Okay, if you don't have the ability to do that, maybe putting a tower up isn't in your best interest. Okay, because if it does fall, now you have to face the consequences of what you overlooked in your planning. Which of the following is an important safety rule to remember when using a crank-up tower? So this type of tower, basically what it is if you see here, it's just a tower retracts into itself with a series of cables and a series of pulleys. So you're down here at the bottom and you're cranking it, and it brings up each section up, and then you keep cranking, it brings up the next section. You crank it some more and it brings up the next section, right? Here's the problem. If those cables are only designed for the weight of the tower, in the tower, those sections above it are only rated at 500 pounds, and the tower itself weighs 300 and you weigh 250, while it's fully extended and you've got your hands on the sections, what you could do is possibly snap a cable, and that tower all of a sudden retracts suddenly, and the two parts of the sections of the antenna could act like a guillotine and take your toes or take your fingers off. So the idea is that you want to fully retract your tower to its lowest level, and then you can climb all these sections, because they can't drop. They've gone as low as they can. Okay, and if you're going to do maintenance on it, if you got to change this feed line or whatever, now it's fully retracted. It doesn't matter how much weight you put on it, these sections can't collapse. Okay, and also it's a good idea that you put a block of wood or a block of steel between the first and second sections, because if this was 4 sections, it looks like 4 sections. If you put a block between the outer, and then the next section, 3 and 4 are not going to fall lower than they're not designed to be able to fall lower than the outer section that supports it. Okay, so what is considered to be proper grounding method for a tower? You want separate 8-foot legs, separate 8-foot ground rods for each leg of the tower, bonded to the tower and to each other. The general idea of grounding a tower is to provide a short, direct path for surges and high voltage to get to ground. You know, if a single ground rod is used, it increases the distance required and drops the efficiency of the ground system. And if the ground rods are any shorter than 4 feet, there's not an adequate enough surface area along the ground rod to handle the typical electrical energy that that a lightning strike generates. You need surface area to help absorb that energy and transfer that energy to the ground. Okay, here's an example of a gentleman. He's using an 8-foot rod. He's using like a fence post sleeve, and he's just driving it down. There are other methods you can use. I can tell you that driving a ground rod is typically one of the most laborious things you'll ever do in ham radio. There is a method that I use. It involves digging a little hole and having a bucket of water. You fill the bucket up, and you slowly use hydraulics to work that antenna, and you'd be surprised, just working it up and down and then pouring more water in it. The force of the rod going down forces the dirt at the bottom of the hole, the pilot hole that rod is creating, it forces it to the sides. And by you doing that, you're pushing the dirt out of the way. You can take an 8-foot pole. I've taken it all the way down to the ground. Sometimes I can only get it down to 4 feet, and then there's a suction action that happens and it stays stuck. And then you have to get out a mallet, or you have to get out a sledgehammer and drive it the rest. But 4 feet is a lot better driving with a sledgehammer than 8 feet. At 8 feet, this thing is it's just vibrating. 4 feet, there's a lot more of it in the ground, providing a base. It doesn't vibrate nearly as much. So again, it's always best. It's not absolutely required, just a best practice, if at all possible, to keep your grounding materials of the same type of metal. Okay? This will help prevent and reduce electrolysis and corrosion and oxidation. Oxidation, not so much, but corrosion and electrolysis, it will. Why should you avoid attaching an antenna to a telephone pole or to a utility pole? Because usually on a utility pole you have power lines connected to it, almost always, right? You may have cable television wire, but typically your cable is going to be, usually, like on my property, I have a telephone pole that brings the 200 amp service from my house to that telephone pole further into my property, and then from that telephone pole it comes into my main breaker panel outside. And on that telephone pole, there's about 3 or 4 wires, and there's a telephone line, and then above that or below that is the cable TV line. Typically, your power line is going to be the highest one, typically, but that's not always the case. And why do they do that? Because being the highest one, the idea in mind is that you are reducing the potential of driving underneath it and making contact with that power line, say with a U-Haul box truck or something. That's the idea being in mind. And again, it should be pretty obvious that any antenna should be far enough away from power lines to avoid accidental contact. And if you ever have to work on that antenna, now you got to climb a telephone pole. Now you're inches away from a high power line. 200 amps is the modern typical load coming into a house. I don't know about you, but I don't want to be inches away from 200 amps. Not at all. So, but if you have to maintain and to perform maintenance on that antenna, that's what you'll invariably be doing if you use a telephone pole. As well as electrical companies can see it as misuse of their equipment, and they can sue you for it. They can criminally prosecute you for because utility services are protected by law. They could criminally prosecute you for malicious abuse or malicious intent of their services. They can misconstrue things and say that you were trying to sabotage something. You know how it works. So, which of the following is true when installing grounding conductors used for lightning protection? Sharp ends should be avoided. Okay. Non-insulated, it really doesn't matter if it's insulated or not insulated, because remember, typically current doesn't travel along the ground wire. And they don't have to be carefully routed. Carefully routed would assume that you may have to take intricate angles and go around objects. Remember, grounding, you want it short and sweet, okay? And short and direct. So sharp bends, which include right angles, they should be avoided. And what happens with sharp bends is it can cause the current to jump, okay? Because if there's you remember, current travels the path of least resistance. If it hits a sharp angle and there's a nearby metal surface, it has the potential to jump to that metal surface, okay? Typically we use non-insulated wire for grounding, but it's not required. We just use it. Again, it goes back to best practices, but it's not a make or break proposition. It's just an advisable thing to do. I don't know why I have lightning. Well, lightning and surges try to find ground by using the path of least resistance. So again, you want to keep your grounding system, conductors in your grounding system, short and straight as possible. Again, short and direct is the key. Which of the following establishes grounding requirements for an amateur radio station or antenna? Really what it comes down to is, because you're dealing with grounding always follows within electrical code. The same electrical code for your house, because that it's attached to your house. Electrical codes vary from across the country, and they can vary quite a bit. The electrical codes for Florida are a lot different than they are for New York, a lot different than they are for Kansas and Texas. In California, you absolutely know their requirements are going to be a lot different. They're probably off the radar. They're off the scale with their requirements, right? So ultimately, your FCC Part 97 does not have anything to do. It gives you best practices, but it does not provide guidelines in terms of electrical code. Okay. If some of us live hundreds of miles away from an airport, so why would FAA, tower lighting matter? Okay, some of us might live near a very small municipal airport. I live 60 miles from Charlotte, and the airport is on the opposite side of Charlotte for me. Charlotte's probably a good, I would say 20 miles wide. I'm probably 80 miles from the airport, or somewhat close to that. 80 miles away typically is not going to enforce, because usually your electrical code is going to be county or state. A lot of times it can be county. Some counties have different rules for grounding than others. In North Carolina, the electrical code on the coast could be a lot different than the code that is in the mountains, in the Appalachian Mountains in Asheville or Boone. So UL recommended practices, that might fly. But usually UL is a testing. It provides testing. Usually you'll see that little stamp that says UL tested, and all they've done is just tested it for fire hazard, all the different things that could cause catastrophic failure, and give it a passing grade if it passes their threshold. So because the grounding system falls under the electrical installation, it's governed by local electrical codes. Most electrical codes across the country use the NEC, National Electrical Code, as a baseline, and then they build from that. You're never going to see a city that has an electrical code that is slacker than the NEC. It doesn't happen. It's always going to be more stricter and more demanding. So you should be aware that local codes vary. They dramatically vary throughout the United States. So, And they also they have different demands. Some localities require that if you put grounding for an antenna that you have to get it inspected. There are some areas that require you to get a permit to erect a tower. Okay? You just have to find out what your restrictions are. Which of the following is a good practice when installing ground wires on a tower for lightning protection? Again, short and sweet. That is the answer. Short and sweet. Short and direct. Straight lines. Okay? Remember, we don't want right angles. So because that isn't the right answer, D, all these choices are correct, can't be right either. Now, it is a practice putting a loop in a ground connection. Well, the problem that throws here is ground connection. You want it straight and direct as possible. But in our feed line, a lot of times we will create a loop of 3 or 4 turns. And what that does is it kind of creates a lightning arrestor. And the idea in mind is that if lightning hits your antenna, travels down to the feed line, when it hits that loop, it'll blow out the loop. So all you find yourself doing is replacing the coax. Okay? So that can't be the answer because you don't put a loop in the ground connection. You can in your antenna connection. So use larger wires over short distance on a direct path to your ground rods. Again, we typically ground wire is going to be 4 gauge bare. Some people use 6 gauge, but the general practice is don't use anything thinner than 6 gauge. The lower the number, the thicker the cable, the thicker the wire. 10 gauge is a lot thinner than 4 gauge. Okay. Now remember, along with that, the thicker the wire, the stiffer it is. So that's why a lot of people go with 6 gauge because it's still flexible, but it has enough stiffness to remain straight and not flop and bend. Bends in the wire may allow the electricity to jump from the wire to nearby conductors, and that really could defeat the grounding system. And whatever it jumps to, now that becomes an issue. And if that isn't grounded rod, you're going to fry something. So again, the longer the wires are, the more resistance there is, and the higher the wire, the hotter the wire can get. Once again, use large wires over short distance on a direct path to the grounding rods. Remember, short and direct. What is the purpose of a safety wire through a turnbuckle used to tension guidelines? So what happens is, let me show you one. Turnbuckles. It's usually an eye loop with screw threads, and sometimes there's an eye loop on the other side, and there is a threaded sleeve that they both screw in. And when you unscrew this, the length of these increase. And usually all it takes is just a wrench or vice grips, and you can turn this. Well, the problem is that sometimes, especially if these are used for guy lines, sometimes with the wind, a guy line can go slack a little and then it can tighten up. Just a little bit of slack and tighten up. And that little bit of movement doing its job, it can cause the sleeve to move. So what they use a safety wire for is it goes through the loops and it wraps around the sleeve. And the idea is that it allows it to keep a bite and keep the tension and keep movement from working the sleeve. It could be very minute, but imagine a good storm that lasts all day for 18 hours. 18 hours of wiggling and moving, you could gain a centimeter on this turnbuckle. A centimeter could cause this guideline to slack. And now you really got some flopping around because one of the legs is not as tight as all the others. Here's another example of them they've gone through each of these eye loops. Okay. So these are only going to turn so far until they hit this cable. Okay. The safety wire doesn't prevent, it won't help. If the turnbuckle breaks, the safety wire is a lot weaker than the turnbuckle. It just prevents the sleeve from turning. It's just too fragile. They won't prevent theft of your antenna, which doesn't, it doesn't think about the effort that goes into theft. But somebody could vandalize, they could vandalize it and make it fall. If you got a neighbor that hates the sight of your tower, he could come over there and essentially loosen these turnbuckles if he knows a storm or hurricane's coming in and cause catastrophic damage. But so these won't, the safety wire won't prevent that ability to do that, because all you got to do is just snip this wire. All you got to do is just cut this wire. Right here's enough gap, just some wire cutters. And now you've removed it. It doesn't have anything to do with climbing a tower, because the safety wire is only used on the turnbuckles. Okay, it has nothing to do, it has no aid in climbing a tower. It doesn't make the job easier. It just doesn't have any, all it does is help maintain the tightness of your guidelines. What type of radiation are VHF and UHF radio signals? Okay, so really, I could see where you might think, have a draw, and it could be any of these, but remember, you remember we talked about the ionosphere? Out of all these, the ionosphere, ionizing radiation, plays into a radio signal. So it can only be, it really makes sense that only two of these, knowing that ionosphere, and it can only be these two. Sound is cutting out. Huh. Not sure why. You have ionizing and sound gone. Okay, did it come back? I just clicked off the microphone and reactivated it. Can you hear me now better on your end, Richard or John? Okay. So what type of guys, by the way, thank you so much for pulling in the long haul. You guys are sticking with it. Again, you came in late, but we're down to the wire here. I've only got maybe 10 more questions, and I really want to finish this course tonight. It wouldn't serve you guys any better to do 10 weeks. I didn't want to do 9. So we're going to knock it out. But I thank you so much for you guys sticking in it and being troopers. So we've literally gone through 2 chapters, 2 and a quarter. We've gotten a lot done tonight. So what type of radiation are VHF and UHF radio signals? Well, they're non-ionizing, okay? So electromagnetic energy may be considered ionizing or non-ionizing. Just remember, ionosphere plays into your electromagnetic signal, which is your radio signal. When radiation is ionizing, it means that it can separate the electrons from the atom to create ions. Lower frequency radiation, which includes all the radio bands, is non-ionizing. So the higher frequencies that you get into, you start dealing with ionizing radiation. High frequency is ionizing. Regardless of the power of the signal, the frequencies of VHF and UHF signals are too low to dislodge the electrons. By the way, gamma and alpha radiation are ionizing radiation. Which of the following frequencies has the lowest value of MEP, or a maximum permissible exposure limit? So they have told you that 50 megahertz is. So experimental data, doing experiments to find the answer, it indicates that frequencies that are easiest for the human body to absorb are between 30 megahertz and 300. Okay, so what they're saying here is that the radiation coming off of an HF antenna is not going to, your body does not absorb it as well, because HF is 3 megahertz to 30. VHF if I were transmitting down here and you were on my roof and you had your hands on my antenna while I was keyed up, you could get burned. Especially, remember, 200 watts is the limit. 200 watts. You know, you can easily see, typically most radios are only 50 watts, but your legal limit is 200. Yeah, if I had it on an amp and I was pushing 200, you go up there and put your hand on it while I'm keying up, you're probably going to jump off of it and pull your hand away. Okay. This means that this range requires the lowest exposure for frequencies between 30 and 300. 50 megahertz is the only one that they offer for you. Just remember, the 30 to 300 is VHF. Okay. It's a tricky question. Okay. It is a tricky question since we're talking about the easiest absorption, the easiest. What has the lowest value for permissible exposure? What is the maximum power level that an amateur radio station may use at VHF frequencies before an RF exposure evaluation is required? Again, you had that last question that told you 50 megahertz. Well, now they're talking about the power level. Okay. So the FCC considers any power levels below 50 watts to not have a significant risk to you for RF burns or interference. So it's issued some rules that are excluding stations that are that transmit at these levels, 50 watts below. So in other words, your Baofangs, that's why Baofangs have kind of slipped under the radar as long, because handheld mobile tends to do that. But usually VHF, UHF, 6 meter, typically all the radios for those that you buy on the market are going to be 50 watts or less. Okay. So when a station reaches or exceeds 50 watts at the antenna, typically the FCC states that an RF exposure evaluation is required. Okay. However, I've never performed one on my radio. I would also say that if you build your own antennas, your feed line is made in a factory. You're not going to make feed line at home. You don't have the equipment and you don't have the means to be able to do it efficiently. And your radios are made in a factory. The antennas are homemade. So the best way to remember that I would find to remember this is that you really don't have a lot of control over the maximum wattage that your radio has. So think of it as it's already been evaluated at the factory. They've already set their models, and before it passes FCC regulations and can be sold, it's already been tested at the factory in a lab for its exposure. Okay, just an easy way to remember. What factors affect the RF exposure of people near an amateur station antenna? Okay, well, first of all, if you're not within the radiation pattern, you're probably not going to be quite as affected to the exposure, right? If you're not in the pattern, then the radiation really is not, your body isn't succumb to exposure. Maybe a little bit, but not very much. The distance from the antenna, that certainly makes, if you're standing 2 feet from an antenna, you stand a lot more chances of getting burned than standing up on the roof next to my antenna than I am down the ground. And obviously the frequency and the power level, again, it goes back to the last question. Frequency plays into it. or a couple questions ago. Okay. So each of these answers affects the person's exposure. If you remember, if you can pick two of them and you're not sure about a third, a great chance that it is all these answers are correct. If you know for sure that two of them are right, doesn't that make sense that probably all these choices are correct? So the frequency of the signal determines how easily the body absorbs RF energy. Your body will absorb 3 megahertz a lot differently than it will absorb 440 megahertz. And as the power level of the signal increases, obviously the energy increases, and therefore the exposure increases. And distance, of course, closer you are to the source, the more exposure that you have, a greater exposure. Finally, the radiation pattern indicates the areas where the energy is directed and how it's concentrated. Every antenna has a different pattern. Every type of antenna. You can buy a G5RV from DX Engineering, and I can make one, and they're going to have similar patterns, but they're not going to be the same. They're going to be a little bit different, just simply because of the materials used. A lot of factors go into that, but they're going to be very close. So a G5RV is going to behave differently than an InFed or a Yagi directional antenna. Why do exposure limits vary with frequency? Again, it goes back to the human body absorbs energy differently at different frequencies. Your body itself has a resonant frequency, just like an antenna does. In fact, really depending on the organ or on the part of your body, you could have a resonant frequency. So, that's where you start getting into MRIs, CAT scans, MRIs. You start dealing with resonant frequency, and the equipment that they use, the modeling and the software that they use already considers that. I'm just going to use an example. Your knees or your bladder has a different resonant frequency to it to provide imaging than your heart does, than your kidneys do. Also, where they're located in the body too. If they're deeper into the body, there's a different frequency there than if it lies just under the skin. Okay. So I'm just giving you a reason why the other answers can't be correct. We're almost done here. I've only got a few more. Which of the following is an acceptable method to determine that your station complies with FCC RF exposure regulations? So one of the ways that you can do that is I've given you a website that you can go to, but they have software that you can download for free that enables you to model your antenna and put in different factors. You put all these different factors, and the model generates a potential radiation pattern for you. What could happen if a person accidentally touched your antenna while you were transmitting? Again, it goes back to an RF burn. An RF burn you'll feel the sensation on your skin, but the damage incurs from the inside out. Okay? It incurs on your nerves deeper in your fingers than on the skin itself. So again, your body acts like a resistor. It absorbs some RF energy, varies depending on the body part and the frequency that it's that your body is receiving. So again, remember, a resistor turns electrical energy into heat energy. It's one of the functions of a resistor. If the body absorbs too much energy, it means that it will create enough heat to damage tissue in the form of a burn. And again, we're talking tissue. So the skin may look fine. You may have a little redness, but you don't see any blisters or anything like you would assume with burns. The tissue underneath your skin, though, could be cooked. So touching an antenna will not cause radiation poisoning because RF radio frequencies is a non-ionizing radiation. So it could cause a burn, but you're not going to die from radiation poison. Okay. Which of the following actions might amateur operators take to prevent exposure to RF radiation excess of FCC supplied limits? Well, the first thing, increasing your duty cycle is not going to. So I'll explain what duty cycle is. It's a ratio between when you key up and when you're listening. The more that you key up, the more of a duty cycle you're presenting, and your radio is working harder. Okay. Relocating your transmitter, that is because your antenna is where the exposure it takes place at. It is what is transmitting the radiation, the signal that's creating the radiation field, not your transmitter. So if you're in the second floor of your house and you have some RF exposure issues, you're not going to solve it by moving your ham shack down to the basement. What you need to do is you need to relocate your antennas, because that's the source that creates that radiation, that field, radiation field. So an RF radiation radiates outward from the antenna. Therefore, it's the antenna that must be moved. Transmitter isn't doing it, has no effect. So increasing the duty cycle will have the reverse effect. It could increase your exposure, because duty cycle is just a ratio of how much time the receiver spends transmitting compared to how much time it spends receiving. One of the feature selling points of a radio is when they say it has a high duty cycle. That means that you can perform a lot of traffic on it. Okay. A duty cycle creates heat. So the longer you talk on a radio, it's a lot like duty cycle on a cellular phone. It's going to heat up. The longer you talk and you use it, you're creating heat. So that's why if you've been talking for a while on your radio, especially on a mobile, you'll hear the fans kick in after a certain amount of time, because the duty cycle is now creating heat. It requires the fan to cool things off so it doesn't cook. Okay. How do you make sure your station stays in compliance with RF safety regulations? So once you use a model and you check your equipment, really the best way is, if you ever change anything in your equipment, you really need to reevaluate and run those models again and plug in the different things, what you've done differently, to get a new model of what your system is doing. Okay. So anytime you change your equipment, it's just a good time to reevaluate things, right? In your car, if you go change out the alternator, you go change out the fuel pump or the gas tank or anything like that, and you're, high performance guy, the first thing you're going to do is reevaluate everything, see if you're getting the same performance as before. You don't need to inform the FCC. Again, it goes back to remind you that we're self-policing. We monitor ourselves. We report each other. We really police ourselves. We address it with them directly. FCC just simply doesn't have the manpower and the funding to go after the small stuff. Okay. Like I told you in several subsections before, the FCC is looking for the money. They're going to go after big dollar offenses. And by the time you see them, it's a lot like the game warden. If you see them, you've been caught. Don't deny it. They've already got enough on you. Now, there's a chance something might be happening and you don't even know it's happening. Okay. Again, be honest, and so the SWR in your system will ensure that there's an efficient transfer of power between your transmitter and your antenna. Okay, that doesn't really have a whole lot to do with compliance. That has to do with your performance. Why is duty cycle one of the factors used to determine safe RF radiation exposure levels? So the duty cycle means if you're keying it up, you're transmitting. The more you key up and the more you transmit, the more you're increasing the exposure to anybody. If all you do is turn on your radio and all you do is listen, you don't ever key up, you don't have to worry about an exposure field. It only comes into play when you key up and are transmitting a signal. What is the pattern of that signal? Because in that pattern is your exposure. Okay. So a person is likely to tolerate a one-time high peak exposure of very short duration than lower exposure over a long period of time. Because again, a period over a long period of time, we're talking about building up heat, right? A short amount of time, yeah, it's a jolt, but there's no heat being created. It's too fast. So, again, this is where duty cycle is important because, again, it's a ratio measurement of the transmit to the receive times. Okay. So antenna and feed line losses and an amp heating up, it doesn't have anything to do with RF exposure. The amplifier is providing power, is amplifying the power. Okay. So they really don't have to do with the RF exposure. There is a little bit of a degree, but when they're talking about, again, if you're increasing the power, but they're talking about the thermal effects. That's internal to your ham shack. If your amplifier gets too hot, it's just going to blow, and it's only going to affect your ham shack. The neighbor it's not going to affect him. What is the definition of duty cycle during the averaging time for RF exposure? So the definition is basically just a percentage of time that the transmitter transmits versus the amount of time that it receives a signal. So again, duty cycle is on and off times. When is it on the air and when is it off the air? Receiving a signal and just listening is considered off the air. All right, the minute you key up, you've gone on the air. And all it is just a ratio between those two. How does RF radiation differ from ionizing radiation? RF radiation does not have the efficient energy to cause So you guys don't hear me? You don't hear me at all, huh? And disconnect. You don't hear me at all? Are you guys getting sound and video again? So how does RF radiation differ from ionizing radiation? So RF radiation does not have sufficient energy to cause genetic damage.